of Canada, the Ottawa Centre. If you have any questions for the speaker, please use the Q&A icon at the bottom of your screen. We're not going to be monitoring the chat box, so any questions or answers. And for this next presentation, I'm going to be asking some questions and expecting some answers. So please use that box to respond. Just about Zoom security. For your security, do not click on any web links that might appear in the chat or Q&A windows for your own safety, and you should be fine there. So this is the schedule for this evening. In about 4 minutes, we're going to be starting off with an introduction to astronomy. And this is for anybody 8 years of age or up. And so it includes adults as well. Then we have Night Vision Changes Everything by Boyan. Portable Astro Imaging Control Room by Paul. You may have heard Andrea this morning on CBC's In Town and Out, talking about her joy of astrophotography and how she doesn't love the moon a whole lot. So be quite an interesting session with Andrea at 8 o'clock. Jim Thompson's going to be talking about how to be an urban astronomer. And then starting at 9 o'clock, we're probably going to go to the cloudy skies version of this, or we'll be showing images, but we'll see. If we happen to get some opening in the clouds, we'll do some live deep sky observing. So we're going to play that one by ear. It's a little hard to judge right now, but there are some clouds rolling in, all part of living in Ottawa. So we're going to get things underway in about 3 minutes. So grab something to drink, do a bathroom break, and we'll be ready to go. Okay, folks, it's 6 o'clock. Welcome back. We're going to start off with an introduction to astronomy. And my name is Dave Chisholm. I'm a member of the RASC Ottawa Centre. And this is a presentation that I've given to many scout groups and guide groups and adults as well. So hopefully you enjoy this. And this is brought to you by the Ottawa Valley Astronomy and Observers Group and the Royal Astronomical Society of Canada, the Ottawa Centre. If you have any questions or you need to respond to any questions that I ask you, please use the Q&A box. And JS is standing by to read those answers out to me. And we should be ready to go. So here's what I'm going to be covering this evening. what's up? What can we see with the naked eye? In other words, without telescope or binoculars. We're going to go talk about what we can see this month. We're going to cover some of the constellations, not all of them, or we'll be here till midnight. How to find north, and then how to find south. If you go to the astrodayOttawa.weebly.com website and click on the virtual IAD 2021, you'll be able to download the handouts that go with this presentation. Included in the handouts is a star finder and the bits and pieces that you need to put it together. There's basically 2 pages. I'll be explaining how that works. So if you don't have it downloaded now, don't worry about it. You can do that after the presentation. So star finders and how to use them. I'll be talking about the different types of telescopes that we use as astronomers. And I'm going to then run a planetarium of the night skies, and we'll walk around and take a look at some of the things that we can see. The good thing about the planetarium is it's never cloudy, so we won't have any issues there. Okay, so first question for everybody who's on the call here. Can you tell me what you can see in the sky without binoculars or telescope, from the brightest to the dimmest? So any suggestions? What is the brightest thing that we can see up in the sky?
Somebody here says the sun.
The sun, that's correct. But you know, many people will say the moon, and they forget that as astronomers, we look at the sun as well. So that is correct. Super, thank you, Roger, got that one. Yeah. Okay, so the next thing, what is the second brightest thing up in the sky? I sort of gave that one away already. Not a star, no. The moon. Good job. Yes, so the moon is the second brightest thing. Now it's going to get a little bit more difficult. We're moving into the planets. So what is the brightest planet up in the sky? The planet is about the same size as the Earth. Any guesses? What's the brightest planet up in the sky? No, it's not Mars. No, Mercury is very, very small, not very bright. But Venus, good. Joanne got that one. Good job. Okay, so we've got the sun, we got the moon, we got Venus. Next brightest planet up in the sky. Jupiter. Yeah, Iva got that one. Good job. Okay, and then the next brightest planet, and that's the only one we can see up in the evening sky right now. The other ones are up during the daytime or middle of the night. Mars, you got it, Cecilia. Okay, and then the last one that we can see without the use of a telescope or binoculars, and I'm assuming this is from yes, Saturn, you've got it. Yeah, so that's from the city. In a dark sky area, you can see some of the other planets if you know where you're looking for. But okay, so we've moved through the planets that we can see. The next brightest thing that we can see up in the skies are, okay, Monica's got it, stars, perfect. Okay, and then we've got the human-made objects that go around the Earth. What do we call those? The ISS, yeah, our satellites, absolutely. So right now we have about 5,000 satellites up there. 3,000 of them are dead. They're space junk. Biggest of those is the International Space Station. And in fact, it's going to be flying directly overhead this evening. So we'll be sort of pausing our events so you can run outside and look for it through the clouds, and the International Space Station. So the next brightest thing that we can see from the Earth, as the Earth goes around the sun, it encounters clouds of dust and rocks, and they burn up in our atmosphere. What do we call those? What do we call those things that burn up in the atmosphere? Meteors, you got it, okay. And then sometimes we move through a massive cloud of dust, and we have what we call meteor showers. Okay, and then the last thing, there was one that we could see last summer in the evening sky. Its name was Neowise. What is that? It's got a long tail. Comets, that's right. The tail's called a coma. That's part of where the name comet comes from. Okay, so those are the brightest things that we can see up in the sky. So let's move forward then. So first of all, the brightest thing is the sun. And if you've been on any of our other presentations earlier today, including my previous one to the younger kids, Never, ever, ever look directly at the sun, even for an instant. Most of the areas of our body have pain sensors. So if I pinch myself, it hurts. I get stung, it hurts. I've got pain sensors everywhere. There's no pain sensors in the eye. So you can look directly at the sun. Your eyes are not going to, they're going to run, but they're not going to tell you that they're actually being damaged. There's no, you don't feel any sort of hurt coming from them. And if you look at the sun for more than an instant, you're going to have some temporary and possibly permanent eye damage, and more than a few seconds, you've got permanent eye damage and blindness. So it's very important that we do, as astronomers, we do look at the sun. We do look at it in a safe way. One of the most interesting times to look at the sun, if you don't have a telescope, is when the moon moves in front of the sun. We call that a solar eclipse. And we're very lucky in Ottawa, we're going to have another solar eclipse. So right on your calendars on April the 8th, 2024. In Ottawa, 90% of the sun will be covered up by the moon. And if you happen to drive down to Kingston, we have what's called totality. And that's where the complete sun is covered by the moon. And that is the only time that you can safely stare at the sun, is just during that middle of the totality. But when it comes to a solar eclipse, we have these really cool glasses. These are eclipse shades. These block out 99.99% of the light. You wouldn't want me driving down your street with these eclipse shades on. I can't see a thing except the sun. We've also got a cardboard version of these as well. And again, these are perfectly safe for looking at the sun. Again, they block out 99.99% of the light. Another interesting project that you can do for the solar eclipse, and the last time we had a solar eclipse here in Ottawa was a few years ago, and a bunch of kids came to the Aviation and Space Museum along with 7,000 others, and they brought a pinhole camera projector. So in this case here, this fellow's taken a cardboard box. He's cut a viewing hole through here. He's cut another hole here. He's put a piece of tin foil over, and he's just put a little pinprick through the foil. The sun shines on that and gets projected onto the back of the box. And that's another safe way to view the solar eclipse, okay? Now, if I want to look at the sun through my telescope, and by looking at it through the telescope, I get a lot more detail. I can see sunspots and various other things. I have a specialized shield that I put over the end of the telescope. And that, again, blocks out 99.99% of the light. And it's now safe for me to look through the viewfinder at the sun. Some older telescopes used to have a fitting that went into the eyepiece. That's the piece that you look through. They're not allowed to sell these anymore. They're very, very dangerous. But if you happen to have an old telescope kicking around, maybe out at your cottage or someplace, and you have one of these, please throw it in the garbage. Okay. The reason being that a telescope magnifies the image, okay, intensifies the light coming in. So if you can imagine, this is a very, very dark coating here on this piece. The sunlight comes all the way down through the telescope, hits this black piece here. It gets heated up, and eventually it gets so hot that it cracks. And now you're looking at the sun magnified through a crack, and you're blind instantly. So these are very, very dangerous. So I always tell people, if they have these in their telescope kit, just throw them away. They're not allowed to sell them anymore. But there are still some of them around. So the moon is always safe to look at. And but the best time to see the surface features is not the full moon. Everybody goes, oh, it's a full moon, let's go out and take a look at it. Well, it's actually very flat. You think about what's happening. The full moon, the moon is on the opposite side of the earth to the sun. Sun is shining directly on it. So if there's any mountains or any craters, there's no shadows. And in order to see the detail, that sort of 3D effect, you need to see some shadows. So let's take a look here. Here is about a half moon. And you can look at this between the dark and the light. This is called the Terminator, which is the line between the dark and the light. Look at all the details that we can see here. We can see all the craters, and we can see some mountain ranges here, and so on and so forth. So the best time to look at the moon, I like to look at like a thin crescent moon. You can see a lot of details. And once it comes to a full moon, yeah, it's interesting to look at, but it's very flat looking. Here's the full moon over here. This is a crater Tycho, and you can see some of the ejecta rays that have come out of this. This is a fairly new crater. It's only about 95 million years old. You got to think of it in terms of astronomy. The moon is 4.5 billion years old. 95 million is fairly new. Over here, this is the Sea of Tranquility. You probably heard about the first landing of the moon in August 1969. Last time we had somebody stepping on the moon was in 1972. But we are having return missions to the moon through the Artemis program. But it's been a long time since we had anybody step out on the moon. These black areas here are flat lava fields on the moon. And this is the area where the first Apollo landed. The other ones sort of landed generally in this sort of area of the moon as well. So planet Venus, in literature, it's sometimes called the morning star. But, you know, Venus is half the year it's in the evening, half the year it's in the morning. And it just depends on where it is in its cycle around the sun and where we are around the sun. But it's so bright that in a really dark location without any moon out, it can actually cast shadows. What we're seeing here are Venus shadows. Now, it's called a morning star. It's not a star at all. Obviously, it's a planet. If we look up in the sky, how do I know if I'm looking at a planet or a star? So there's a couple of ways that I can tell that. Anybody know the answer to that? Yes, correct. Planets don't twinkle. So the twinkling is caused by the interference in the Earth's atmosphere. Planets have a more intense light, so that they don't tend to twinkle. So that's one way. Another way is that certainly some of the planets are much brighter than any of the surrounding stars. Certainly Venus stands out, and Jupiter. Saturn, not so much. Saturn looks like an average star, but again, it doesn't twinkle. The other thing we have to think about too is that if you're looking north from here, you're not going to see any planets. The planets tend to travel over the equator. So you're going to have to be looking south in order to see the planets from up here in Ottawa. So they tend to travel across the southern sky from left to right, from east to west. Okay.
There's a question here from Monica. She says the northern lights also counted as one of the brightest things in the sky.
I must admit I've never sort of considered that because there's such a rare occurrence down here in Ottawa, but certainly they're very bright in the northern regions. So yeah, certainly that would be one of the brighter things. But it's a rare event to have them down in the Ottawa area. But good question, thank you. Okay, so planet Venus. Okay, so then we got planet Jupiter, the largest of our planets. And ever since we first invented telescopes and pointed them up at Jupiter, we've seen this red spot here. This is a huge, huge storm. It's going on for over 400 years. It was about 400 years ago when the first telescope was pointed at it. Sometimes it gets a little bit bigger, sometimes a little bit smaller. 3 Earths can fit inside of this storm. It's absolutely huge. And the planet Jupiter has 79 moons going around it, but it doesn't have the most moons. And it is a gas giant. So basically, it's a big ball of gas. There is a small central core, but it's not a rocky planet like Mercury, Venus, Earth, or Mars. Or Pluto, which is a dwarf planet, is also a rocky planet. Okay. Now, with a pair of binoculars or a small telescope, we can actually see 4 of the largest moons of Jupiter. Okay, and sometimes you don't see all of these 4 moons. Sometimes one appears to be missing. It's either in front or behind the planet. And but most times when you look up at Jupiter, they appear to be, they look like little stars all in a line adjacent to the planet. Again, they don't tend to twinkle like stars.
Dave, a question here. I think it was related more to Venus, but Roger asks if it's not safe to look at the sun, is it safe to look at the morning star?
Yeah, so it is safe to look at Venus as long as Venus is far enough away from the sun. Often in the evenings, Venus is moving towards the evening now. It's perfectly safe to look at, but sometimes Venus is very close to the sun. So that's you can certainly look at Venus. And when it comes to when it comes to looking at Mercury, every once in a while, Mercury will set after the sun because it's normally very close to the sun, and that's happening later on this month. I'll be talking about that when I do the Ottawa skies for the month of May. So there are opportunities to see Mercury, and it's a very small pinprick of light, and you'll see it just in this month. It'll be just after sunset. So the planet Mars It's not a very big planet. If we take two of our moons and lie them side by side, they would stretch across Mars. And looking at the evidence that we've seen from various probes that we've sent to Mars, it appears as though Mars at one point had oceans, and it had a much better atmosphere than it's got now. It's got a very thin atmosphere. And what we think happened was billions of years ago, whatever created the magnetic fields within Mars and Earth, we've got a spinning molten mass in the middle of our Earth that creates the magnetic fields, the North and South poles. Those magnetic fields actually really protect us from the sun's damaging rays. And when the sun's rays come towards the Earth, they get deflected around the Earth by the magnetic field. Mars lost that billions of years ago. And as it lost it, the sun then stripped away all the oceans, stripped away most of the atmosphere. So it's a very desert-like planet right now. We've got two new probes that have landed on Mars. We have the Perseverance rover, which landed on the 18th of February, thereabouts, 18th or 19th of February, along with the Ingenuity helicopter. And yesterday, China just confirmed that they've landed a rover on the planet as well. And it's not moving yet. They're just doing some initial tests, but it's going to be quite exciting to see what they come up with. It does have polar ice caps at the north and south poles. It has two moons, Deimos and Phobos. Deimos is a regular sort of orbit around the planet. Phobos has a really wonky orbit. It goes twice as fast as the planet spins. It travels very, very close to the planet. And we figure it's going to break up at some point in the next 100,000 years or so, and either crash into the planet or just break into small particles. It's a fairly small moon. It's not going to do a lot of damage. It might create a new crater or two on the planet. Planet Saturn, this is one of my favorite planets with all the rings and so on. And the rings are visible even through a small telescope. I have a 3-inch telescope. No problem seeing the rings, not to this level of detail, but I can certainly see a white dot with a ring around it. Okay. It has the most moons. It's got 82 moons. The largest moon of Saturn is Titan. And we believe there's a possibility that that moon could support some sort of life form, as does one of the moons of Jupiter, Europa. Europa appears to have an ocean under its crust. So the next brightest thing up in the sky are the stars, and the brightest star that we can see is Sirius. Now, Sirius is a wintertime star. If you can imagine Orion and Orion's belt, the 3 stars in Orion's belt, if you slide down Orion's belt and head down towards the edge here, you're going to encounter Sirius. Sirius is now moved further south because we're moving into the summertime. But in the wintertime, it is very, very bright. So that's the brightest of the stars. There are Arcturus and Vega or some other bright stars that we can see year round. So this is part of what we call the constellation Canis Major, or the big dog. This looks to me more like a headless person than a big dog. When we go to the actual constellation contains a few more stars. The head of the dog is here. The neck of the dog is here. These are the feet. So, but this is the dog constellation Canis Major, the greater dog. Satellites. So the brightest of the satellites is the International Space Station. It will be visible tonight. It's flying directly overhead. I think it's around 10:15. But the folks who are doing the presentation at that time will pause. And if it's not cloudy, they'll send you outside and tell you where to look for it. So it is sometimes brighter than Jupiter when it's up there. And but we've, since 1957, when the first satellite went up, which was Sputnik, we've put up around 5,000 satellites. 3,000 of them are dead. They're space junk. Some of them have crashed back to Earth. So we've only got 2,000 that are working right now. But one of the problems that we're having is that there's some new companies out there, Starlink being one of them, are putting up satellites so that everybody in the Earth can have internet, which is a great idea. But the problem we have with astronomy is that every one of those internet satellites has solar panels like this. And so what happens, the solar panels are obviously used to power the satellite. So what happens is the sun hits the solar panel, they collect the energy they need, and the rest of the sunlight gets reflected down to the Earth as a little pinprick of light. So if you've ever been out in a nice dark area and sort of lay down in the field and looked up, you can see the satellites going overhead. Well, in another 10 years or so, we're going to have 15 to 20,000 new satellites going up around the Earth. And it's going to be very difficult for us to look through our telescopes and see anything past those satellites into deep space, because they're always going to be photobombing our pictures. Now, what we have been working with the manufacturers of those satellites, we've asked them to put a shield on. If you can imagine this part that's sticking out here as a bit of a sun shield. So when the light hits the solar array, there's a bit of a shield there to block it from shining down to the Earth. So we're hoping that they're going to make that modification shortly so that we do not have a lot of issues. So meteors are the next thing. And as the sun goes around the Earth, as the Earth goes around the sun, let me get that right, it encounters clouds of dust. And if there's a really dense cloud of dust, we have what's called a meteor shower. And those are very, very predictable. There's different times in the year where we know there's going to be a lot of meteors. And this is basically like a grain of sand that's burned up in the Earth's atmosphere. And it's very, very fast. It's just like that, and it's gone. And sometimes, however, the pieces are big enough and they make it all the way through the Earth's atmosphere, they hit the ground, and they become a meteorite. So there's a tons of different locations where these are. This is one of the ones that I like. This is in Argentina, Campo de Cielo, which means sky field. There was a large iron meteorite hit the Earth there and broke into many pieces. This one's the size of a car. This is typically the size, or what they look like. It's an iron meteorite. And I even have a piece of it right here. So this is a rock from space, and there's a magnet. Sticks to the magnet. Okay, so that's an iron meteorite. Now, back when we had the dinosaurs, there was a meteorite that hit the Earth. It was about the size of the city of Ottawa, and it landed off the coast of Mexico, and it sprayed up a lot of water vapor and dust into the Earth's atmosphere, so much that it blocked the sunlight for a period of time, for a number of years, killed off a lot of the vegetation, and wiped out the dinosaurs. So those are very rare meteorites, and we've actually got a bunch of telescopes that are monitoring for any object that's going to that size that's going to be near us, and hopefully we'll be able to intervene and push it out of the way. So I don't think we need to worry about that in the near future. So the other thing we have are comets. So this is the most famous of the comets. This is Halleys Comet. Next time it comes around is in 2061. And we actually had a visible comet last summer, Comet Neowise. And it was visible to the naked eye. Most of the time, in any given year, we can see 5 or 6 comets from Earth. Most of them are very, very small, very faint. You need a big telescope to see them. But every once in a while, we get a really great show like Comet Neowise. So this one comes around in 2061. I'll be 103 then. I'm going to go out and see it. So let's see what's happening in the Ottawa skies for May. Well, first of all, here's the phases of the moon. On the 11th of May, you may have heard that Ramadan is over. Well, this is the Muslim schedule is based upon phases of the moon and their calendar. So this was the moon that ended Ramadan, and so that's the new moon. And this is what the moon's going to look like tonight. And then as we move through here, we're going to be having a full moon. And I just have to, 26th is the full moon for the month. It's sometimes hard to tell from these images here. And this is what's called a supermoon. It means the moon is slightly closer to the Earth. Really, I can't tell the difference between a supermoon and a normal moon. It's really not significantly larger, but it is a closer approach to the Earth. And this moon was known by the early Native American tribes as the flower moon, because that's the time of year when spring flowers appeared in abundance. It's also been known as the corn planting moon and the milk moon. Okay, and this is the second of 3 supermoons we're going to be seeing for 2021. The next one is next month. Here's the sunrise and sunset for the month. So we're midway between these two. So as you can see, the days are getting longer. The longest day is going to be June the 21st. Mercury, remember I said that you can't see Mercury for the most part, it's too close to the sun? Well, May the 17th, look for in the planet low in the western sky just after sunset. Okay, it's going to look like a little pinprick of light, and you'll be able to see Mercury on the 17th of May. Venus is now visible after sunset, and so you can look for it in the evening sky. Mars is visible all throughout the evening. Jupiter is visible before sunrise. So these are this is the rise and set times on the first, rise and set times on the 31st. Saturn is also visible before sunrise. Uranus is visible before sunrise the second half of the month. Right now it's rising and setting with the sun. And Neptune is visible before sunrise. Both Uranus and Neptune are very difficult to see, except through a large telescope. Interesting thing about Uranus, most planets spin this way. Uranus got knocked over when the solar system is being formed. It spins on its side. It's got rings like Saturn, not quite as spectacular, as does Neptune. Neptune has rings and it spins in the normal way. So we're going to go through all 88 constellations, and JS will be pleased to know we'll be finished by about midnight. JS is monitoring things. No, we're not going to go through all of them. We're going to go through some of the constellations. So this is a bit of a test. Constellations is where us human beings have connect the dots with the stars and come up with various images up in the sky. So let's take a look at some of them. Anybody know which constellation this is? Any guesses? Big Dipper, good. I've got that one. So this is the Big Dipper. This is probably one of the easiest ones to spot up in our northern skies. A little interesting thing about the Big Dipper. At this point in the bend in the handle of the Big Dipper, there are two stars, Alcor and Mizar. And way back in the Roman times, they wanted to check the eyesight of the Roman soldiers. They didn't have the fancy eye charts or eyeglasses like we have nowadays. And they didn't want to give a soldier any bows and arrows if they couldn't see properly. They might shoot the wrong side. So what they did was they took the soldier out, they had him look up in the sky, and they said, look at the handle of the Big Dipper. How many stars are there? If the person responded, there's one star, they were given another task, not the bow and arrows. That's a quick Roman soldier eye test. Okay, so this one's a little more difficult to spot. The stars are not quite as obvious, but this is Polaris. This is the northern star. Anybody know what constellation? And Monica got it right away. That's the Little Dipper. Yeah, yes, and that's correct. The Big Dipper is not a constellation. It's called an asterism. It's part of a bigger constellation called Ursa Major. So, okay, and this is Ursa Minor, the Little Bear. So there's the Little Dipper. There is the now, a lot of people think that Polaris is a really bright star, and it's not. It's an average-looking star up in the northern sky. It sits right above the North Pole. So sometimes it's a little bit tricky to find, and I'll show you in a couple slides how we find that one. This one is a big W in the sky. It's the seat of an Egyptian queen. Does anybody know what constellation that is? Good luck trying to spell it, but you can at least give it a try. Begins with the letter C. Cassiopeia, yes. Cassiopeia or Cassiopeia. There's two different ways of saying it. So it's a big W in the sky. And I just noticed here that the galaxy has photobombed my image there. That's the closest galaxy to us. That's at Andromeda right there, just under the A of Cassiopeia. Okay, so how do we find Polaris? Well, the easiest way is to use the Big Dipper and draw a line like this all the way up, and you're going to encounter Polaris. If the North Pole's at 90 degrees north, and the equator is at 0 degrees, where is Ottawa? Does everybody know how far north Ottawa is? It's between 0 and 90. Just take a guess. Any guesses? Okay, so Ottawa is 45 degrees north. Okay, so we're midway between the equator and the North Pole. So what that means is that this is the equator and this is the North Pole. Polaris is 45 degrees up in the sky. So that's another way to know if you're looking at it. Okay. Yeah, Montreal is also at about 45 degrees. Okay, so that's how we find Polaris. There's Cassiopeia to just sort of give you a reference as to where things are in the sky. This is a wintertime constellation. It's now setting with the sun. Anybody know what this one is? Orion, you got it. Yes. Yeah, so this is, there's Orion's belt, and there's the spheres, there's the shield. This is an interesting, this is a red giant. This is Betelgeuse. And way back at the end of 2019, Betelgeuse started to dim. And when a star starts to dim, that's not a good sign. That normally means the star is dying away and it's going to explode into what we call a supernova. That's a very, very bright event. And the thing just blows up, and it's so bright that sometimes you can even see it during the daytime. So as astronomers, we were getting very excited about the fact that maybe Betelgeuse was going supernova. And so as we sort of went out of 2019 into 2020, we were getting more excited, and the pandemic hit, and Betelgeuse returned to its normal brightness. So we're not really sure what happened. I read an article in one of the astronomy magazines, and somebody has speculated that there was some interstellar dust either created by the star or went in front of the star for a period of time. Anyways, it's not going to blow up anytime soon. Down in this area, we have what are called nebulas, which are large clouds with stars in them. And this is like a star nursery area right here. This is the Orion Nebula. There's a bunch of other really interesting things in here as well. This one is a little hard to spot. So I'm just going to take you straight to the constellation itself. There's just so many stars in this image here. So this is Cygnus the Swan. And you can see here the wings of the swan, there's the tail, there's the neck. And then I'm going to zoom out a little bit, and Cygnus is still going to be there, just out a little bit further. And I've now brought up two of the constellations that are fairly close to each other, Cygnus and Lyra. Lyra the Harp. Now, why do we learn all these constellations? Well, these are like signposts that we use to find other really cool things up in the sky. So if we can find the constellation, and then we know that there's something really interesting next to it. So for example, Lyra here, and Lyra's got a really bright star called Vega. It's right at the top here. So it's not too hard to find Lyra when it's up in the sky, because it's got a very bright star at the top of it. And I know that if I look in this part of Lyra, there is a star that went supernova many, many years ago, and it's left behind the remnants called the Ring Nebula. And the original star has exploded, and then it shrunk to a white dwarf, and that's right in the middle there. That little white dot, that is the star as it is now. Okay, but by using the constellations, I'm able to get my telescope and point to that, and I can look at the Ring Nebula. Okay, so you find yourself in South Africa, Australia, South America, and you're trying to find north. Because of the curvature of the Earth, you're not going to be able to see Polaris, so you're going to be able to find south. Unfortunately, there is no star over the southern pole, so you have to do a little bit of math here. So what we use to find south is that we use the Southern Cross. Now you may recognize this pattern of stars here. These are the stars that are on the flag of Australia and New Zealand. Okay, this is called Crux, is the other name for this constellation. So in order to find south, you draw a line through the center of the cross all the way down to the horizon. Then you go across the arms of the cross, and you're going to find two fairly bright pointer stars, Alpha and Beta Centauri. And these are some of the closest stars to Earth, by the way. And you draw a line at right angles to that. And where those two lines meet, that is the South Pole. So you got to do a little bit of math there. Now, another interesting thing is that if we want to look at planets or the moon or the sun, we have to look south in order to see them. So in Canada, if I'm out in the evening, I can watch the moon go across the sky. It's going to go from left to right. Okay. But in Australia, in order to see the planets and the moon, we got to look north. So in Australia, when you look up in the sky, things move from right to left. Now this sort of hit me. I was visiting Australia back in 2018. Got up at 3 o'clock or 4 o'clock in the morning to watch a lunar eclipse. And that's where the Earth blocks the light to the moon, and the moon turns a reddish color. And it just happened to be happening when I was down there. So I got up in the middle of the night, and I'm looking up in the sky, and I was very puzzled because the moon was going the wrong way. Then I had to think about it for a couple of minutes and realized, okay, I'm in the southern hemisphere. I'm looking north. Okay, so here you find yourself down in the southern hemisphere, it's quite amazing to look up in the sky, because there's a lot of constellations that you can't see that we see up here. The asterism, or the Big Dipper, the asterism called the Big Dipper, or the Little Dipper, those are visible down there. You can't see Orion, but Orion's standing on his head. Orion's upside down. Okay, so as I mentioned at the start of my presentation here, if you go to the web page that we have for this particular event, which is astrodayottawaweebly.com, click on the virtual IAD 2021. There's a bunch of handouts there. One of those handouts is a PDF file. It contains 2 pages, and this will allow you to build your own star finder. So basically, I like to print it on cardstock. It works better that way. So first thing you got to do is cut out the wheel. The next thing you got to do is you're going to cut out this part of it, and you can see there's some tabs here. And then what you're going to do is you're going to cut out the center oval, cut out the tabs, and there's dotted lines where to fold the tabs. I'll fold these tabs over like this. And this is going to be the pocket. And inside that pocket, I'm going to put my wheel. Okay. So I've got one already put together. I just tape it shut with some Scotch tape. So there is my star finder right there. So first thing we've got to do is we've got to dial the date and time. So we're on the 15th of May, and I'm going to go to 9 o'clock. So let me just find the 15th of May, 9 o'clock on my wheel here. Okay, so I've now dialed the 15th of May. It's not very well in focus here at 9 o'clock. Okay, so now I've done that. Next thing I need to figure out is which way is north. Well, if I'm outside and I'm looking up at the sky, I know how to find north now. I use the Big Dipper and align up to Polaris. But in my office here, I know that north is directly behind me. So let's pretend I'm outside. I've got this thing called the northern horizon. So I'm going to tip the northern horizon up behind me, and I'm going to look up. And now I can see what constellations are up there. This does not tell me what planets are up there. They follow their own patterns, but there is a black line in here that tells you the path of the planets as they go across the sky. Now, one of the challenges with these star finders is that you're really tempted to get out your bright white flashlight and shine them on the star finder. Well, if you're out in a really dark location, the pupils of your eyes get really, really big, and you get what we call night vision. And we'll be talking about that in the next presentation as well. And we need to protect our night vision, because the more light that we can bring in, the more details that we can see. Turning a bright white flashlight on this is going to destroy our night vision. But as astronomers, we've learned over time that red light does not destroy our night vision. So what we do then is we use a red light to look at things. And you may wonder, well, where do I go get one of these really cool red light flashlights? Well, you could go to an astronomy store and spend a pile of money, or you could do as I did. I went to the dollar store. This was $1.25. I bought 2 of them. This one is colored red, a red Sharpie, just colored in the lens. And I've got now a red astronomer's flashlight. Okay. The other thing you can use is red nail polish. That will work just as well. Okay. And I actually use these red flashlights when I take my scouts out on night hikes. I encourage them to bring red flashlights with them, even if we're not looking at the stars. It allows them to keep their night vision on, and the red light is plenty bright enough for them to be able to see things. You'll also see here that the Milky Way, which is the center of our galaxy, if you look in here, is shown on here. And Cassiopeia, the W, is right in the middle of the Milky Way. Now, from the Milky Way is really obvious when you're in a dark sky location. There's so much light in the city that it's very rare to be able to see the Milky Way. But boy, you get up in Algonquin Park or into any of the dark sky locations, it's absolutely amazing. It just jumps right out at you. The other thing that we have in the handouts here is the evening sky map. This is published by a company in the States called skymaps.com. Absolutely free. They publish the next month's map about the last day of the previous month. So at the end of May, if you want to get the June sky map, just go to the website, skymaps.com, and you can download it. What I like about this is that it works exactly the same as the star finder that I just showed you. But what it does show me is it shows me where the planets are. So right now at this is for 9 o'clock in late May. So we're probably looking at 9:30 right now. We're middle of the month. This is where Mars is. So it does show me where Mars is on here. There we go. Okay. And it works exactly the same way. You just flip it up with the north pointing north. It tells you what other things that are happening. So I can look on here and I can see that on the 11th, it was a new moon. And on the 26th, there's a full moon. And then this one says there's a total eclipse of the moon, but it's not in our area. Okay, it's in another part of the world. And anyway, so Mercury, remember I said we could see Mercury? There it is right there, greatest elongation east, which means that you can see it. I don't know why they call it the greatest elongation east, because you actually have to look in the western sky to see it, but that's part of the nomenclature. On the back of this, there's some tips for observing the night sky, things seen with the naked eye, things you can see with the binoculars, things that you can see with a telescope this month. Okay. The other thing that we have in the handouts here are astronomy websites. So I'm a member of the Royal Astronomical Society of Canada at the Ottawa Centre. We do host star parties May through October when there's not a pandemic going on, and we meet at the Diefenbunker parking lot. So that's on hold right now. And we have monthly meetings on the first Friday of each month at the Canadian Aviation and Space Museum. And again, we're meeting virtually via Zoom. So if you go to our website, you'll find all the information for that. There's a bunch of other local astronomy groups listed here. We have a web application called the Clear Dark Sky. It was actually written by one of our local astronomers here, but it's used across Canada. And we can go up there and it will predict how much cloud cover there is and how the scene is. Sometimes there's a lot of high winds in the upper atmosphere that impacts our ability to see things clearly. This will predict that about a day in advance. We do have a dark sky area. It's about an hour and a half from here near Plevna, Ontario, the other side of Perth, out Highway 7. It's an official dark sky preserve. People in the immediate area are not allowed to have any lights pointed up into the sky around their houses. It's an excellent location if you want really dark skies. If you want to find out when the International Space Station is coming directly overhead, this is a really good website, heavensabove.com. You also can tell when, you could also ask a sunrise, sunset, planet rise, planet set as well. But the key thing about this one is make sure you tell the software where you are located. It assumes you're off the west coast of Africa otherwise. Okay, so just make sure you tell it where you are located, then you'll get accurate information. When it comes to the International Space Station, it's only accurate about 10 days out. Okay, you can't go much further than that, then it's not that accurate. Skymaps.com, that's what we just saw right here. We have a Canadian publication, comes out every 2 months, called the Sky News. It's published by the RASC, and it's available at your local chapter's store. And when it reopens. And then this is a free software called Stellarium. And this is an excellent piece of software you can put on your PC, Mac, or Linux system. And it's a planetarium for the night sky. And it's really, really well done. And I'm going to be using that in a few minutes. And then the other thing is, well, where do I go to buy a telescope? Please don't go to Walmart or Costco and buy the $29.95 special. You're going to get really frustrated with that. You want to get a good quality telescope if you want to get into astronomy, and you don't have to spend a pile of money. But there's about 4 telescope stores across Canada, and we have the best one in Ottawa. It's a small company called Focus Scientific. They're on Merivale and Bentley roads, and they are just, all the local astronomers go to them all the time for their service and support. You can probably get started with a telescope in the $150 to $200 price range. Okay, so these are the guys I would go to if you're interested in getting into that. So talking about telescopes, the different types of telescopes. So basically when it comes to a telescope, the bigger the opening, the longer the tube, the better the image. This is a very rough way of dealing with things. This one's got maybe about a 3-inch opening, maybe a 2-inch opening. Light comes all the way down the tube, bounces out off the eyepiece, the diagonal mirror here comes out the eyepiece. That's the original telescopes for something like that. And then this one over here, the light comes all the way down to the bottom, bounces off a mirror, comes all the way back up and comes out the eyepiece. This is making the tube twice as long as it would be, so it makes it a little more portable. And then the one at the bottom here is exactly the same configuration, except it sits on the ground. This eyepiece here is about 2 meters off the ground, so you need a step ladder to see. And the light comes all the way down, bounces off, comes out the eyepiece. This one here is what's called a Schmidt-Cassegrain. And this one, the light comes all the way to the bottom, bounces off the back, comes all the way back up, bounces off another mirror, goes all the way back down. So it's 3 times through the tube. So it's like you got a tube 3 times as long. This is also a computerized telescope. So when I set this one up, what I do is I have to tell it where I'm located. So longitude, latitude, date and time, and so on and so forth. And then I can just take that little keypad that looks like a telephone on the side there, and I could say point at Jupiter, and it will go, and it will point up at Jupiter, and it will track Jupiter as the Earth turns and as Jupiter moves across the sky. These other telescopes that we see here are all manual, which means that about every minute or so, you're going to have to adjust them as things drift out of view. The other type of telescope that we use are radio telescopes. This is the Algonquin Radio Observatory. It's the 4th largest radio telescope in North America. It's up in Lake Traverse in Algonquin Park. It's currently being run by a group out of York University. It was, they're leasing it from the federal government. And I know quite a bit about this particular radio telescope because my dad was a radio astronomer and worked on it shortly after it opened in 1965. So the parts of a telescope, you got your opening, aperture. So the bigger the opening, the better the image. The optical tube, the longer the tube, better the image. You've got a focuser. So this is the eyepiece. You're looking through the eyepiece and then you're focusing. You've got the mount, which is normally a tripod of some form. And you've got this little telescope on the side here called the finder scope. And most people with their first telescopes, they don't know what to do with this. They sort of wonder, well, why do we have this thing on here? The finder scope does not have any magnification. It's normally just a plain piece of glass, and it's often got like an X etched on it, or it's got a little projected light, either a little red dot or a little bullseye that projects onto the glass. What you do is that when you get the telescope out, is that you align the finder scope to the eyepiece. So you point at like a tree in the distance, the very top of the tree. You get the X lined up in the, or you get it lined up through the eyepiece here, and then you tweak some screws on the side of the finder scope, and so that the X sits in the same spot as you're seeing through the eyepiece. This saves you a ton of time because if you can imagine, I'm trying to look through the regular eyepiece with so much magnification. It's like looking through a little straw, looking across the sky. So I'll show you how it works. So I'm trying to look at Saturn. So what I do is I get Saturn in the middle of my finder scope, right, like this, and then I can look through the eyepiece and boom, there it is. It saves me a ton of time. So getting back to radio telescopes. So this is the Algonquin Radio Observatory. And I had the pleasure of being able to visit it a number of years ago. Our family actually went up and had a family reunion up at the Algonquin Radio Observatory because we'd never been there. My dad worked on it when I was fairly young. And unfortunately, he passed away a few years after he did his work on the radio telescope. And we always wanted to see what it was that he was working on there. So my family and a bunch of astronomers from Toronto came up in the middle of August one summer. We wanted to be able to see the meteor showers as well as the telescope. And they were very nice. What they did was they took the telescope and they leveled it out so that we could actually climb up on the side. You can see the size of the telescope here. That's my family right there. And my mom, she was 83 back then. She was the oldest person to ever climb up onto the dish. And it's not an easy climb. There's a lot of gangplanks and step ladders and stuff to get up here. So that is the Algonquin Radio Observatory. Well, what did they do with that? Well, the Canadians were the first in a particular thing. Scientists had proposed was that if you had one radio telescope in one location and another radio telescope in the other location, if they could link those two telescopes together, it was like you had a radio telescope that was as wide as the distance between them. Okay, it's a similar sort of concept when we talk about the bigger the opening in the tube, the longer the tube and so on. Well, this is a huge opening. And so there was a race on between the Canadians and the Americans to see who could do it first. And we were doing it between Algonquin Park and Penticton, BC. There was 2 radio telescopes. And back in these days, this was the mid-1960s, they didn't have the internet or anything like that. They actually used videotapes that they used in the TV studios to record the signals and the timing. And then they brought the videotape back from Penticton back to Algonquin Park, and they played the two tapes together, and they were pointing at a pulsating thing called a quasar, and they were actually able to image that. And the Americans were racing to get it done first, but we beat them by 6 weeks. So we were the first in the world to do that. It's called very long baseline interferometry. And since then, we've used done a lot of work with that. And a number of years ago, all these radio telescopes right here were all linked together, and they were pointed this direction towards a black hole. They wanted to get an image of a black hole. Canada wasn't involved because the image was down here and we were too far north. But all these radio telescopes got linked together. They synchronized all their signals. And so first of all, I want to show you what an artist's impression of a black hole is. And this is sort of looking from the side, and we're going to look from the front. And this area here is a black hole is basically a collapsed star. And it's collapsed so much that even light can't escape from it. The gravity is so strong. This is the event horizon where the light is coming into the black hole. And I mean, if you think about it, the Earth, if it were to be pulled into a black hole, just to give you an idea of the power of the black hole, the whole Earth pulled into a black hole will be shrunk to something about that size. You don't want to get anywhere near a black hole. Okay, so what was the image that they got here? That is the image, first image ever of a black hole. They did this using a very long baseline interferometry, which I would say is a Canadian invention. We're the first ones to do it. So that's a really cool thing. Okay, I'm running very short on time here. I'm going to quickly go into Stellarium. You can download this from stellarium.org, do a quick tour of the night sky. And just give me a second here. What I like about this is there's never any clouds. So this is what Ottawa looks like right now. There's the sun. It's about ready to set. And what I'm going to do here is I got lots of superpowers in the software, so I'm just going to move the time forward to, let's move it back a little bit here. We'll go, yeah, about to 9:15 or thereabouts. And I'm just going to freeze time. Oops. Is time frozen? Yes, it is. Okay, there we go. So there's Arcturus. There's one of the brighter stars up in the sky. And let's turn on some constellations here. Okay, I'm going to turn on the constellation names. So we've now got our signposts labeled in the sky. Makes it much easier to navigate. Now we've got the Gemini twins here. And there's actual pictures that go along with these as well. You can turn those on, but I find they sort of get in my way. Let's take a look at inside of Gemini. We've got both the Mars and the Moon right now. They're very close together. So there's what the Moon looks like tonight. It's moving from a new moon towards a full moon on the 26th. So there's the Moon. And then we slide up here. We've got Mars. Okay, so there's Phobos. Remember, this is the moon with a wonky orbit. It's going around twice as fast as Mars is spinning, really close to the planet. There's Deimos, the other moon. Okay. Now, by using the constellations here as signposts, I can go in and I can look for things. There's Cassiopeia, and the Andromeda is down here. It's a little bit out of the picture. There is Lyra and Vega, one of the brighter stars. And remember, I said if I zoom in here on Lyra, there we go. Okay, so this is the remnants of a collapsed star. And we'll keep spinning around here. So there's Ursa Minor. So there's Polaris, the North Star. And where is Ursa Major? There it is. It's further up in the sky there. So there's Ursa Major, the big bear. So that looks like a bear. There's the nose. There's the feet of the bear. Most bears don't have tails. I don't know if any bears have tails, but maybe the astronomers don't know their anatomy. Anyways, there's the line that you draw right there. And I know that if I go off at the handle of the Big Dipper here and zoom in a little bit, I'm going to encounter what we call the Whirlpool Galaxy. Okay, these are interacting galaxies. There's actually two galaxies here. That is a really cool image. Okay, so I'm using the pointers of the constellations to navigate my way around the sky. Now I'm quickly just going to move the time to 4 o'clock in the morning. There we go. And we'll just move around a bit here. And at 4 o'clock in the morning, now we can see Jupiter and Saturn. So there's Jupiter. And we can see the 4 largest moons of Jupiter. We've got Io, Callisto, Europa. We think there could be life in Europa, Ganymede. Jupiter. There's Jupiter. The red spot is not there. Jupiter spins just like the Earth does. The red spot's on the other side of the planet. Okay, and we'll just go find Saturn. There's Saturn. And there is Saturn. There's Titan, the biggest moon of Saturn. Could be life on there too. There are the rings of Saturn. This is called the Cassini division, the big break in the rings here. And there's a little break in the rings out here, and I believe that there is a moon that sits inside of that ring, and that's what's causing that break. So Saturn has the most moons. It's got 84 moons. Jupiter only has 79. Okay, I'll show you one more thing here, if I can find it. Just give me a second here. I'll zoom out. Okay, so the closest galaxy to us is the Andromeda Galaxy. Remember, it photobombed my picture of Cassiopeia. Cassiopeia is up here. And there is the Andromeda Galaxy. Okay, so that is it. This is Stellarium, Stellarium, and goes to stellarium.org, and you can download that. So thank you very much, folks. And
thank you very much. And I see we have next Beaujean, who is going to be speaking about night vision changes everything. And I will highlight.
There, I've got it for you.
You got it? Okay. Thank you.
Thank you. Let me just get sharing here. That works. Awesome. All right. Thank you, Dave. That was a great presentation. So Dave alluded to this in the previous presentation, and I didn't think there could be a dual purpose to the word night vision, but I guess there is. So Dave spoke about night vision and how our pupils dilate in astronomy. And if you're in a very dark setting, your pupils will get bigger. And if there's a light source that is bright, your pupils will get smaller. And that is an aspect of astronomy that is very important. However, the night vision that I'm going to be talking about is the night vision that you would think about in movies. So commandos wearing night vision on their head and the use of that in astronomy. So this is a niche part of astronomy. Everyone in astronomy is basically doing either nighttime astronomy or solar. However, this night vision component is a small subset of us astronomers. So that's what I'll be talking to you about today. So a quick primer on night vision astronomy and why it's important to me. So this was me 14 years ago at our probably astronomy day at Chapters at Blair with my first telescope that my parents bought me. And I was absolutely thrilled. It's an 8-inch telescope, and I was pretty excited because, you know, I thought I could see a lot of things, a lot of objects, and a lot of detail. And to be frank, I am part of the millennial generation. I see something in a magazine, and that's kind of what I'm expecting to get at the eyepiece. So lo and behold, I get my star chart, go out into the countryside, plop down my telescope, and then the brochure is on the left. This is the North American Nebula, or what it would look like if you were superhuman. And then you get to the eyepiece. So look to the left, look to the right, look to the left. Unfortunately, the image on the left is a photograph. So someone took a very sensitive camera, took a picture for probably 6 to 8 hours, or perhaps even multiple evenings, and then stitched it together in Photoshop, and then put that in the sky chart. And then you're trying to look for this, and in reality, unless you have a very big telescope or some special video equipment, you're going to be seeing with your eyes what's on the right. Now, I live in a condo type thing. I don't have room for a backyard observatory, so that part's out. I also don't like driving out into the countryside when I want to just observe for maybe 20 minutes or 30 minutes, what my schedule allows. So this is where night vision changes everything. So what are the factors that actually affect our view when we're at the eyepiece? And I'm just talking your eyeball, the eyepiece, and a telescope, no other fancy things going on. So we have dark adaptation, which is the first thing, which is if you're in a dark setting for 30 minutes, that's about how long it takes for your pupils to fully dilate, usually 7 to 8 millimeters. And that lets your eye capture more light into your eye so that you can see those faint fuzzy galaxies that are far away. This is actually a factor of age as well. So the older you get, the less elastic your pupils are. So they can't dilate as much. You can't get as much light into your eyes, and your ability to resolve faint objects goes down. Location is simply fixed. It's where you want to observe from. So are you willing to drive an hour into the country, or are you watching from the city? Size of the telescope is obviously the biggest factor. So if you remember some basic math class, the area of a circle is pi r squared. So the bigger your diameter of telescope, the more light it collects, the brighter the image is. Pretty straightforward. Light pollution is another factor. And if you're viewing in the city, your telescope actually starts catching some of the light from streetlights or neighbors or just the glow of the city, and that reduces the contrast of the object you're trying to see. So that's another thing you have to battle when you're trying to view just with your eyes at the eyepiece. Another component is the atmosphere, and what that is imagine if you look straight up, there's about 100 kilometers of air between you and space. So there's a bunch of light coming in from space through the atmosphere, and it's kind of uninterrupted for the most part as it travels to the space. But as the light enters the atmosphere, there's air currents, there's the jet stream, there's humidity in the air, there is volcanoes that erupt. I spoke to an astronomer who actually works for Environment Canada earlier this year, and he said that already now we can forecast that there will be a lot of forest fires out in BC that will release an immense amount of smoke into the atmosphere. That smoke travels around the world and degrades the image in actually very noticeable ways. So that's another thing that we have to contend with when looking through the eyepiece and not using special cameras that we talked about. This, I'm not sure if it's been talked about today, averted imagination. I'm being a bit cheeky here, but this is averted vision. So through our evolution of the human species, our eyes have evolved to be more sensitive to movement for reasons that you can probably imagine. So if we look at a stationary picture, our eyes can see a certain amount of detail, but if you shake the picture, you will see and register more details than you would normally. So this is actually a trick that we use as astronomers. Quite literally, you'll be looking through your eyepiece and you will hit your telescope or kick the mount to shake the telescope. That will move the image and you will actually see a bit more detail depending on how hard you kick it. All the mitigations that I've talked about on this page are really shades of gray. There isn't really one thing that drastically changes anything except the size of the telescope, which is what we're going to tackle with night vision. The last piece is spectral range. from my earlier presentation at around 1, we talked about the visual spectrum of light and how you can only see a very small spectrum of visible light, which is what our eyes register. However, a lot of these really cool objects out in space actually are emitting light outside of those ranges. So either in IR or UV. And there is certain amount of information there that we would like to see, but our eyes simply don't register it. So that's why back in this North American nebula, which is probably releasing most of its light in the hydrogen range plus infrared, we don't see any of the infrared, which is why you're more likely to see the picture on the right than the picture on the left. So finally, after that primer, we all understand what we're contending with for visual astronomy. So what is night vision? So in the past 20, 30 years that it's been around in its sort of modern structure, it's been exclusively used by militaries as what's called a force multiplier. And I'll putting that in quotes because I'll be bringing it up later in the astronomy setting, where if you take 2 soldiers, put them on the battlefield, equipped the exact same way and have the exact same training, but one has night vision, aka one can see at night, the other one can't, that is a force multiplier. So you have a unit of something that you want to do something with, but that unit is multiplied in terms of force because it can see at night, it can actually do things at night, as opposed to someone who wouldn't be able to see anything. What I would like to emphasize, and this is also important, is these night vision devices are not magic. They don't create light out of nothing. So if you go into a pitch black room and there's no photons in that room, there's no image to amplify, and you will get a dark image. This is why all of these night vision devices actually come with an IR flashlight built in, and you can activate that IR flashlight. It bathes everything in invisible IR, and that could let you see in a dark room. Not really useful for astronomy. Actually, you could use it to read your charts, but you could read your charts with just the night vision without the IR flashlight. So a quick primer on how does night vision work. So photons, or we can say light, of all wavelengths enter the front lens. So usually on most night vision devices, there is a lens at the front. However, not all housings have a lens. And the photons strike a photocathode tube here and at the front of the tube, and they convert the photons to electrons. So this is no different than a solar panel. If you want to simplify it a lot, this is a mini solar panel here that receives all wavelengths of light and converts the light into electrons. The electrons at step 3 travel through a microchannel plate. This is just a fancy mechanism that takes the electrons that are representing the light that entered, amplifies the light using a battery that's inside the housing, usually just a AA battery, and multiplies the number of electrons. So it bumps up the voltage of the incoming signal. This then hits a phosphor screen, which is at step 4 here. And it's, if you've worked with this type of phosphor before, but anyways, if you hit it with an electron, there will be a bright flash, and that bright flash is actually representing the image that started all the way at step 1. However, it's just amplified a lot more due to the fact that the electrons were amplified here. And then you put your eye at the eyepiece here at step 5, and you see a green image of the original image that came through the eyepiece. For the careful observers here, you've noticed that we've gotten green, red, and blue light coming in, but only green out. So we lose all that information. There's no more color coming out of the night vision. We are effectively taking a color image, converting it to monochrome as if we were with a camera, a monochrome camera. What's interesting to note is for the past 30, 40 years, we've used green phosphor just because that was available. It turns out that the operators who actually use this in the field have said that the green light is very intense. It fatigues their eyes. So recently, basically any newly manufactured night vision device will be white phosphor. So you'll see a black and white image, and it's a lot more pleasing on the eyes. So we know what night vision is now, and how does that help us mitigate some of these challenges that we have in visual observing? Dark adaptation. So we cared before, you're out in the fields, your eyes are dark adapted, your pupils are dilated, and then, okay, you need to check your phone or you need to check something. The instant you look at a bright light, your pupils shrink and you have to wait another half hour. With this, it doesn't matter. You're looking at a bright amplified image in the eyepiece. So it doesn't matter how big your pupils are, or for that matter, it doesn't matter what age you are. You're looking at basically a bright representation of the original image. Location can't change. So this is up to you if you're still planning to view from the city or in the country. That's just not part of this discussion. This one is critical, and I'll go into a lot more detail about this one, but a small telescope becomes a big telescope, and a big telescope becomes a very big telescope with the night vision. Light pollution, we now actually have what is effectively a very sensitive camera, and we can throw on narrowband filters to filter out light pollution and to increase contrast on some of those nebula that we were talking about. Atmosphere, we're not solving that problem. Go to space maybe one day. Averted imagination, we're no longer shaking the scope or trying to look beside the object to try and see if we can gain a bit more data out of there. And spectral range. So our eyes are in the visible spectrum, which is 400 to about 680, 690 nanometers. Now we have a full range that we are amplifying of 400 to 1,000 nanometers. So we can see the deep IR. So how do we measure some of the performance of night vision? And if you were to buy some, where would you look and what performance metrics would you look for? We have our signal to noise ratio. The unit for that is unitless. And that is simply the ratio of your signal. So that is the incoming light from the galaxy, if you will, compared to the noise that is being registered by the sensor. Typical ranges are from 25 to 36, and what you would be looking for astronomy would be something that is higher than 30. Resolution, this is, there's actually, if you go into greater detail of how the night vision works, there's a grid pattern of where the electrons actually hit. So at the front of the night vision, the photons hit this grid pattern where the photons get converted to electrons. That higher that resolution, the more pleasing the image when it comes out the other end. That unit is linear pairs per millimeter, ranges in 64 to 72. You want the higher one. Majority of night vision devices have automatic or manual gain. That is simply, you can change the gain setting on the night vision device on how much those electrons are amplified, how much brighter the image is on the other side, and you want manual gain simply because this lets you dial in any small, basically as the night vision device gets brighter, there's more noise. This is just how electronics work. So you can turn down the gain to compensate for that noise. So if you have a very faint image, faint object, you can crank up the gain. If it's already a bright image, you can turn down the gain, still have a bright image, but get less noise. FOM is something you will hear very frequently. It's the figure of merit, which is the signal to noise ratio times the resolution. So the first two metrics simply multiplied together. Typical range 1800 to 26. You would want something that's higher to 21. EBI, equivalent background illumination, measured in lumens per centimeter squared. This is simply your noise floor. So all of these electronics have an inherent noise to them. This is dependent on temperature and the quality of the silicone that was used to create some of this. In short, you want that value to be as low as possible. Sometimes if your object is very faint and it's below your noise floor, you'll just never see it because your noise from the device is actually louder or higher than the actual signal coming from the object you're trying to look at. Blemishes. So like in all electronics manufacturing, there are certain yields that come out. So if you buy a CPU or a GPU for your computer, certain ones are more overclockable than others. And that is simply due to the manufacturing process. So the silicone that is inside those chips, there are imperfections, impurities, and that simply prevents certain cards that are similar from performing the same way. In the same way, manufacturing process here is imperfect, and there are actual black spots that appear on the tube. This really degrades and takes away from the image. You'll be looking at a galaxy, and there's this constant black blotch on the side of your field of view. You don't want that, so you're looking for a tube that has no blemishes. And then the last metric, which is luminance gain, which is simply the energy of the light coming in versus divided by the energy of the light. Sorry, other way. Light out divided by light in, and that is also a unitless measure. It's a very loud airplane. And that gain, which is the whole system gain of light out over light in, is from 60,000 to 80,000 a multiplication factor, and you are looking for a value that is higher than 65,000 for astronomy purposes. So housings are very important. So we just spoke about the actual tube inside the housing that does the magnification, but how do we actually connect that tube to the eyepiece? This is a PVS-14, frequently used in the military and is very common, can be found on the used market, and usually has a manual gain knob. However, the only challenge is this front lens here is fixed, and I'll talk about briefly why that's an issue later. There is a Mod 3C, which is an American design for a tube, for the housing, with a removable front lens. So you can take the front lens off and expose the light path from your telescope directly onto the surface of the intensifier tube. And this is a French company that designs night vision, and it's a similar design. You can unscrew this front lens and expose the image directly onto the tube. So finally, that was a lot of preamble to get how do we use this night vision in astronomy? My favorite way, and this is where this thing shines, is my favorite telescope, if you will, is this. I don't know if this even shows up, but it's about the size of my fist. There's no setup time, there's no cool up time. I just go outside, point it up at the sky, and there's a picture I took in this unit right here of the night sky of the Milky Way. So you can see beautiful detail in the Milky Way, structure that you can't normally see with your unaided eye, simply because our eyes are not good at this. If you have a housing where you can remove the front lens, then you can actually screw in C-mount SLR lenses into the front, and then again, point it back up at the sky, and you're running. This is a picture of Comet Neowise last summer that I took again with this setup. If you have a unit that the front lens is removable, you screw in a C-mount adapter and you plop it directly into your telescope, and you use the night vision at prime mode. And that is the third option. The fourth option, which is shown in this picture and it looks like a mess, I will go over in the next slide. It's afocal mode, and there are actually benefits to doing this. So this is my trusty 8-inch scope. You remember from the first picture from that first day at chapters that I'm still using. And this is a Teleview 55mm Plössl. And it turns out Teleview is actually in the night vision space. However, for reasons it's perhaps not well known, I'll go into that as well. There's a Teleview to PVS-14 adapter, so I can screw in my night vision directly into the eyepiece. And then the night vision sits on top of all that. Now, why is afocal actually great? If I was doing just regular visual observing, the exit pupil of this configuration, you'll trust me on the math here, is 11mm. This is actually a problem. So this means the image that's coming out of the eyepiece is 11mm in diameter. However, I mentioned that the maximum dilated pupil of an adult person is about 7mm. So you're actually losing a bunch of light that's not entering your eye, which is important. However, with night vision, this is actually exciting. So the front lens of the PVS-14 is a 27 millimeter f1.2 lens. The way optics work is if you take a lens and you stick it onto a lens, the entire optical train actually becomes the effective ratio, F ratio, of the night vision focal length divided by the telescope exit pupil. And what that means is when you do the math, my entire 8-inch f5 scope has been turned into a focal reducer by this optical train. So my 8-inch f5 scope plus the eyepiece plus the night vision is now running at f2.45, which is really exciting because the image scale shrinks and your object is now smaller in the eyepiece. However, all that light is concentrated into a smaller area, so you get a brighter image, plus you're using night vision, so it gets even brighter. So really exciting. TeleVue actually sells an adapter for this eyepiece and converts the 55 into a 67. Same math applies, and we get down to f1.8 on an 8-inch scope. There's quite a bit of coma at that speed, but the views you still get are pretty damn exciting. Filters, if you've been reading between the lines, we actually have a super sensitive camera, and the integration time is 0. There is no more integration time. You're not exposing for 30 seconds, a minute, 6 hours. You are live viewing through this thing. And the fact that it's so sensitive means we can use filters. So I have a 685 nanometer IR pass filter, which works great at cutting out light pollution. And I use that for around the city. And then we use various H-alpha filters in the 3 to 12 nanometer range, which really give amazing views on nebula or any H-alpha object. And it really improves the contrast. So finally, I've talked your ear off. What can you see? You can see so much more. So this is a friend over in London, England, who has a night vision device. This was taken with a smartphone at ISO 50 and a 20-second exposure. And this is the Orion Nebula and Barnard's Loop from a low light pollution area. And you can see the Rosette Nebula here off the left. I'm going to run through these quickly. I believe this is the Rosette Nebula taken through a 130 millimeter telescope, a 20-second exposure at ISO 50. For those of you who do some photography, you can understand just how difficult it is to image some of these things. And we're doing it with a smartphone and an ISO 50. And this is the Horsehead Nebula. Again, same exposure. And you see the types of views we're getting. Now, these views are better than what you would get at the eyepiece due to the increased contrast of the photography, but the visual views we get at the eyepiece are not too far off. Here we've switched to my green phosphor tube, obviously. So this is just a shot with my regular Samsung smartphone through the night vision looking up at the sky. And this is actually pretty representative of what I see when I'm looking at the eyepiece. This is the Orion Nebula. It's not a great photo, but again, I've shown some people the Orion Nebula through this configuration, and it is mind-blowing just how bright it is. And this was Comet Neowise again last summer, somewhere in Algonquin. Again, you look up at the sky and everything comes to life. You see satellites that are magnitude 4, 5, 6 that you can't see naked eye, but the whole sky just comes alive because the night vision just amplifies any light that comes through. And it really shines if you're in a dark area like this. This is entirely anecdotal. I'm going to tell you what I saw because my photography skills with my smartphone aren't great. But with the setup I mentioned previously, the Leo triplets at magnitude 10.3, 9.7, 9.4 were bright. Like there wasn't like any averted imagination. I think they're there. Maybe I'll kick my telescope. No, they were there. And magnitude 13 and 14 galaxies were easily visible. And that's with an 8-inch scope. Globular clusters, you actually need to turn down the gain because they are so bright. So it's really exciting. So this is the key that I wanted to show you. And you watch this YouTube link on your own time, but this is Al Nagler from TeleVue talking about the powers of night vision and how his 85 millimeter teleview telescope behaves like a 10-inch telescope. So this is all anecdotal. I should put a giant asterisk here, but in short, a 85 millimeter telescope becomes a 10-inch telescope. That is a 9x factor in area of the objective lens. So when you scale that out, use that same math, an 8-inch telescope, which is what I'm running, feels like a 24-inch telescope. And here's the limiting magnitude with night vision and no night vision. If you are one of the people who has a slightly bigger telescope at, say, 14 or 18 inches, that 18-inch telescope is collecting about as much light as a 54-inch telescope. And this is the method I'm using to calculate the limiting magnitude of no night vision versus with night vision. So again, big asterisk here, this is entirely anecdotal. This is what people have said. Hey, I have an 85 millimeter telescope, and when I plug in some night vision, I can see what I can see with about a 10-inch telescope. So if I use that same scaling and multiplication, because it is linear, 10-inch telescopes behave like 30-inch telescopes, 24-inch telescopes behave like 72-inch telescopes. So it is extremely powerful. And what you can gain from this is, I don't like carrying my telescope around. I don't like setting up and tearing down and traveling for hours on end to view. However, my 8-inch telescope now behaves like a 24-inch telescope. If you like chasing fuzzies and finding that magnitude 20.3 galaxy, your existing large telescopes will probably get you there.
So Bojan, I wanted to ask, what is the price of this?
Could you believe I have a slide on that?
Okay, fine. That was a question.
Yeah. Running a bit behind on time. In short, US laws, ITAR is International Traffic in Arms and Regulations. So these are US laws which limit the export of tanks, grenades, fighter jets, and believe it or not, night vision as well. So obtaining night vision is a bit more complex process. However, I will let you read this slide on your own later. However, it is possible to get night vision in Canada. So to answer the question now, where and how much? Hopefully you're all excited. You're opening your wallet. You're just looking for the buy now link. Yep, I see some nods. There is a used market in Canada for lower figure of merit night vision. And this is what the airsoft community uses to play at night. So they hook up the night vision to their airsoft guns and then chase each other around in the forest. That's the same night vision I use and I'm holding here, and it works really well. However, it is the used market. So depends how you feel about that. If you would like to export some of that night vision from the United States, you need to get permission from the State Department, which is a 2-3 month process. And you actually need paperwork saying who you are, what you're going to be using it for, and then the United States government needs to give you permission to export that night vision from the United States into Canada. Problem is, no vendor actually wants to sell directly to you in the United States. So you would need an intermediary to actually purchase it for you and legally export it for you. This is not something you want to circumvent. You want to follow the rules on this one. The last and only option, as far as I know, is OVNI, which is a French company. They use German intensifier tubes and put it in a housing of their choice. And that is used for astronomy. So the front lens is removable. So you can have afocal and prime mode plus SLR lenses. And finally, how much? I know you're asking me. Here it is. If you're an astronomer, your garage probably looks something like this. You have 25 eyepieces with some fancy nitrogen purged, long focal length, super wide fields. You have half a dozen telescopes with tracking mounts and cameras. And the reason I'm showing this slide is because you can finally sell a lot of this stuff to finance the night vision. You don't need super special eyepieces. You don't need 6 telescopes. You really just need 2. You need one for the smaller grab and go, and you need a large one for when you're willing to actually set that up. You don't need tracking unless you want to do photography. You don't need any guide scopes or cables or anything. So there's a lot of equity there for you to find to finance this. And finally, to answer that question, the Canadian used market for lower performance night vision is about 38 to 4,500 Canadian dollars. That is perhaps the easiest option. There are new options in Canada. However, I can't recommend the price to performance ratio for that one. They charge $7,000 to $8,000 for new night vision, but the performance isn't there to justify that cost. If you are going the American route, I think I may actually try this and see how far I get with the State Department, but the cost of a new astronomy grade setup is 4,800 US or 6,000 Canadian. And in the OVNI scenario, the French company that takes the German tubes, they can sell to Canada. And these are the various levels of performance and the price in Canadian dollars as of today. So from $7,000 to about $13,500, which is quite excessive, understandably. However, I can vouch that some of these things really do change our visual night vision game. That's everything I wanted to cover. Thank you.
Okay, thank you, Beauchamp. That was really interesting. It almost sounds like a James Bond film. I mean, how do you get this equipment? That's amazing.
I mean, once you're done with the astronomy, you can, snoop through the forest with your night vision and walk around at night.
Okay, well, what I'd like to do is to just bring up the schedule that we're for the following few hours. And I believe that's right here. So you've heard from Dave Chisholm speak regarding introduction to astronomy. And Beauchamp just gave an interesting topic on night vision changes everything. Paul is up next at 7:30 to speak about beginner astrophotography with got that wrong. Portable astro imaging control room. And then at 8 o'clock, beginning astrophotography with simple tracking setup by Andrea. And at 8:30, how to be an urban astronomer by Jim. And at 9 o'clock, it looks like we're going to be moving toward the image gallery since the sky's not looking too good. But please keep in touch because the images you're going to see are going to be really amazing. And we're also going to have information regarding each image that you'll look at, whether it's live or photographed. And it looks, and I see that Dave, that Paul is ready. So that's fantastic. I'm going to just move this over here. Let's see how we do that.
Paul normally doesn't turn on his video, so I put his picture with my on my video there.
Okay, so Paul is not ready yet. Is that what you're saying? Okay.
Oh no, I'm ready. No, it's just Dave was mentioning that I usually turn off my video because of my limited rural bandwidth.
Okay, I see. All right. So
I just wanted to wave and let you know that I'm here and live and well and ready to go whenever you are.
Excellent. Okay.
So yeah, there's no questions for Beauchamp?
No, there aren't any questions on
Okay.
screen right now.
All right, I shall start sharing my screen then.
Excellent.
Can you see that?
Yes, I can see it.
Awesome. Okay, perfect. There we go. Just going to move things out of the way here.
All right.
All right. And do a little test here. Okay, good. All right. So hi, everybody. I hope you're enjoying the presentations tonight. It's certainly been an interesting collection of bits and pieces and lots of information. As you've probably gathered, folks that do astro imaging and observing in general, we tend to be gearheads because it's necessary. It's either our equipment or the supporting equipment that we use it all comes together to give us a pleasant night under the stars. I myself am predominantly an astrophotographer. I do a lot of visual as well, but by and large, the bulk of my stuff is astrophotography. And I live out in the country. I have a very nice dark skies here, but one of the problems I have in my site is that I also have trees on my property, and they limit some of the horizons that I can access with my cameras and telescopes. I do have a permanent dome set up with my main telescope, which is an 11-inch Celestron Edge HD, and a variety of different cameras that I use with that. But as I say, some of the issues I have with trees are they limit parts of my horizon, and they certainly limit the lower parts of the sky. And so as a result, I've had to be a bit innovative. I'm usually out anywhere from 70 to 90 nights a year, depending on how many clear nights we get, and how much other aspects of life like to steal my astronomy time. So I want to make the most use of those. I usually, when I do my astrophotography, I have targets in mind that I like to work with. I do some extended projects, sometimes that span over a year. But I also do sort of off the cuff things, like when we get the Comet Neowise, hey, you got to go where the action is, and so I'm often out in the field as well to access those types of targets. One of the things that we have to deal with here in Canada is, surprise, it's our weather, and winter, as we all know, can be rather harsh here in Canada. Unfortunately, it's also the time of year when we have the longest nights. Here in the latitude of Ottawa, for instance, coming up next month at the summer solstice, our true night, if we don't talk about the moon, but our true night around the summer solstice is just around 3 hours long, which is pretty short. Conversely, in the winter solstice, it's the bulk of the day. It's I think we're pushing like 16, 17 hours. So needless to say, those are nice long nights. We can get a lot of imaging in. Also, the winter skies tend to be free of a lot of the dust and the haze that we see in the summer. So when we get clear nights, they can be very, very clear and very, very dark. So to take advantage of that, when I'm being frustrated by the trees, I wanted to build or get something to use as a shelter, so that I can stay out in the rather harsh environment we have sometimes, and do my imaging. And so I originally talked about this, or originally when I designed this presentation, I referenced my device here, my creation, as a control room, portable control room for astrophotography. But as you'll see in my presentation, it can actually have multiple uses. So I've changed the title. It's a multi-purpose shelter for astrophotography. So I'm just going to show you what I got and what I use it for. This is well, I'll show you the setup actually in a few minutes in another slide there. But just want to back off on this one. This is not an observing tent that I'm talking about. There are specific tents available on the market for observing. These are tents that typically have a closed room at one end, and another section with, as you can see, especially in the Explore Scientific tent there, where you've got a telescope poking out through the top of your tent through an opening. So these are great devices. Kendrick's also used to make one for a few years, which I believe now is discontinued. Pretty sure it is. Explore Scientific is current. Actually, I pulled this image off the current issue of Sky and Telescope, so I know that they're alive and well. And then just Googling on the internet, I found that there are some other manufacturers, I believe European, but that's not what I wanted to build here. I actually have built an observing tent in the past. This is one of my early creations there from about 15 years ago, where I took a tent that I could use in the summer. As you can see, there's a lot of screen windows, and I built it so that I could run my 10-inch Schmidt Cassegrain off one end of the telescope. Actually, can you see my cursor moving when I do this?
Yes, I could.
Okay, super. So you can see that the telescope is sitting here. This is actually an opening, but it's all screened in. So this is what I actually put together for the first Venus transit back in 2004. Where I was shooting this was, I gave it the affectionate name of the Kingdom of the Black Flies, because I know that it could be pretty brutal. And I'm glad I did this, because it was pretty brutal. I think we were the only living things on that hill other than the black flies there. And so if we hadn't been protected, our bones would be rusting out in that field. But that's a summer type of observing tent. You know, with the screen mesh, that's nice to sit out there and not be bothered by the insects and have a nice view of things, but not very suitable for the winter. So what I wanted for the winter was something that I could set up in very, very short time and would provide protection for me from the elements of certainly the cold temperatures that we deal with in the winter, and also the sometimes harsh winds that we have to deal with. So what I did is I based it on this particular unit. This is actually an ice fishing shelter, a pop-up ice fishing shelter from Rapala. And it comes in two different models. As you see, I've circled the larger model, the 3-man version, and for a good reason, as you'll see in a minute. But this tent actually sets up in very, very short order, as I'll show you, and is very generous inside. It has free floor space of 6 feet by 6 feet. And from the inside edges, you'll notice the unusual shape. It kind of looks like a cube, but it's got distended sides. And inside, at the maximum diameter from one wall to the other, it's 90 inches by 90 inches, which again comes in very handy for the other use that I have for this thing. So yeah, this is available. I believe Sale still markets these, or still sells these. Probably Cabela's there as well. And you can get similar ones from other manufacturers. Very handy device, made from very, very strong fabric, much denser fabric than what you would find in a standard tent. So I've used this thing out in howling winds, and you feel absolutely no wind at all coming through the walls there. It's a very rigid structure, but it's also very lightweight. So I'm just gonna show you a couple of images here. This is one of my first tests of this when I got it in the winter. Actually kind of looks a little bit like the lunar module when you look at this view, but needless to say, yeah, this is a real treat in the winter. You can see the shelter set up here. The camera that I was using that night, basically just a Canon camera with a telephoto lens on a Star Adventurer with auto guider, and all being run from inside. A couple of quick views that I just took that night. You can, and I'll show these in a bit more detail in a couple of minutes here, but you can see just looking in through the entrance there. I've got a chair set up there and a table with computers there, a little bit closer view here. I've also strung up, this was just a set of little LED Christmas lights, little blue ones there, to help with my night vision, or to help me, not with my night vision, but to be able to see things inside the tent without having to turn a flashlight on. But as I noticed too, this fabric is completely opaque to light. So you can have a blinding, brilliant flashlight in here, and you will not see this from the outside. And that's really handy when you use something like this in a place like Starfest, where people will frown on you if you're running computer monitors, and that will glare through the fabric of your tent. So that's the other time. That's one of the other places where I've used this is at Starfest, and needless to say, I didn't irk anybody. So this is a winter setup. I'll show you the Starfest one here actually. So this was one of my criteria is setting this up quickly, because in the winter, you know, I just talked about observing tents too. The last thing I want to do is spend, you know, half an hour slamming up a tent with tent poles and pegs and all the rest of this. Not when it's minus 15 or minus 20 degrees. I needed something that went up fast. And this goes up, well, they advertised that it goes up in 60 seconds. And you know what? They're pretty much right on with this thing. We had a time-lapse camera set up we like to do this kind of thing, me and my chum James there like to do this kind of thing at Starfest there. We'll do time lapses of everything, including our operations at night with the telescopes, but even setting up our camp here. So we set up our camera, and we set it up to take images at 1 minute intervals. And I found afterwards that just was too short, because you can see the file times, the image timestamps here. Watch how quickly this went up. And this is not an exaggeration. So this is 1622, 1623, 1624. It was up in 2 minutes, literally. It's quite cool the way this pops up. And I've got some detailed slides here I'll show you in a second about how this actually gets deployed. But needless to say, it's not an exaggeration, and it's a rigid structure. I mean, it's a tent in that, but the way it's built, with the poles that basically pop out, they're all on the inside, makes it a very rigid structure. The poles are fairly good diameter, and so it'll take a lot of wind when you've got this thing pegged down. We had an occasion to test that in the fall, which I will get to in a couple of minutes. But needless to say, it's a very solid structure, and this is basically our setup. This was our setup at Starfest 2 years ago, and this was my original intent for it, was to use it as a control room for my to set up my computers, and also to have a warm place. And the other application I had was I wanted something that wasn't just good in the winter, but was also good in the summer for various reasons, like bugs that I mentioned. Black flies and mosquitoes can, depending on the night, can take some of the excitement out of being out all night. Anyway, this is my typical rig here, with using the shelter. I have solar panels, about almost 300 watts there, charging a deep cycle battery, 120 amp hour deep cycle battery. And to that, I've got a pure wave, sine wave inverter up to 1,000 watts. So I can power pretty much anything. They do supply power at Starfest, but certainly not in all corners of the area of the fields that they use. And also, if I'm out in other places, and I do take this to other places, like People's Hill and some of the other choice observing spots that we have here, there is no power, and so you're on your own. So if you're planning to spend the night there, you have to make sure that you've got enough power. But this setup seems to cut it okay for me so far. So I'll show you. This is just another view with me, just to give you some scale. You can stand up inside of this unit, and you will not bump your head. It's got 6 foot clearance. I know it looks a little bit like I would bump my head here, but once you get inside there, there is ample headroom there, at least for me, and I'm 6 foot even. All right, so to set this thing up, I'll just show you, breeze through some of these. It's pretty quick there. You get it out of its bag there, and it's all tied up. I've got the elastic cords to secure it there. It comes with a pretty generous bag there. You essentially just set it up on its legs there, and then take the straps off. It starts to unfold by itself, like the legs come out. And unlike some of the structures that you've seen, like the porta potties and other instant setup tents there, this is not something that you have to do like geometric origami with to set it up. It actually is super simple to set up. Once you open it up like that, it actually kind of wants to sort of fall down on itself and open up. And you wind up basically just pulling on the lanyards. There's 4 lanyards, one for each wall. And you basically pull them up and they pop out. They pop out immediately and form the structure there. So it is just, there's one at the top there as well. But depending on how you tackle it, you don't have to do it a certain way. You just need to be able to pull one of the lanyards. As soon as you start pulling one of them, the structure starts to pop out itself and assemble itself. So that's the basic structure there. And it's got a nice generous opening inside there. And so to that, you can add things like your accessories. As I said, it's got a 6 foot by 6 foot clear floor space, bulges out to 80 inches by 80 inches on the inside walls there. And so I use essentially just, a usual fold-out camp chair and an aluminum table like this. These are like 27 by 27. There's all different types that you could put into this because you've got the floor space. This is just, it's very easy to assemble, and it's very portable when it breaks down, and gives you a good amount of workspace to put your gear onto. There you can see the inside view. I've taken this with a sort of a wider lens here, 16 millimeter. You can see the chair and the table with a couple of computers. I typically run 2 computers when I'm out in the field like this, just as a backup in case one of them gives me grief or something like that. I can run my complete setup with just one of these. So having the backup is nice. It keeps me from having a problem where everything else comes together and then the computers for some reason don't work, or one of them doesn't work, and my session is lost there. So just it's always good to have a backup plan. And you could actually fit in this floor space you can see here. You can actually fit 2 of these tables quite easily and 2 of these chairs. So if you're observing with a buddy and stuff like that, there's plenty of room. In fact, one of the things that we did at Starfest on one of the cloudy nights is, in addition to my equipment here, we set up yet another computer that was our home theater, and we watched science fiction movies. So good thing to do on a cloudy night. A little bit of a wider angle view. This is with a fisheye lens there. Again, you can see the amount of floor space is quite generous inside here. All right. One of the other things that you can do is run heaters in the wintertime. And this is, I have tested this. Also, I have to backtrack for a second here. This is not my original idea. I got this idea from Taras Rybarski and Andrew Brown a couple of years ago when I met them for an observing session up at Plevna there. They had teamed up there and chipped in, and they had bought a similar structure like this, and we were using it for the same purpose. And I thought, geez, that's a brilliant idea there. So I can't take credit for it. They gave me the idea, and I just kind of went on this, and I'll show you some of the modifications I've done here in a minute. But like them, I also run a heater inside this tent in the wintertime. And again, like I said, the fabric on this material is quite thick, and it'll retain the heat. In fact, one of the worst nights that I was out with this, it was about minus 24 degrees Celsius, and I was running this catalytic heater in there, 3000 BTU, and the temperature stayed at about plus 15 degrees inside and minus 24 on the outside. So a lot more comfortable to work with in the middle of the winter when it's some 40 degrees warmer than it is on the outside. Taras also mentioned that he used something like a buddy heater here, a similar type of thing, but this is a catalytic one, which is in terms of producing carbon monoxide is safer for use inside. These ones are okay in a structure like that too, provided you have adequate ventilation. And if you're going to run a heater like this, I would certainly recommend either a catalytic or non-catalytic heater. I would certainly recommend having a carbon monoxide detector in there just for your peace of mind, because that can be weird stuff. But these heaters are great. Taras said he was running his, and one of the standard butane or propane bottles there, I think there's 16 ounces or so. He said it ran at full tilt for about 4 hours and kept them nice and warm there. So definite bonus when it's very cold out, but very clear out, and you don't want to lose the night. All right, the other thing I found with this is why I call it a multi-purpose shelter, is that I also found that it makes actually a pretty decent tent. It's not intended for a tent because it has no bottom. It's open at the bottom, unlike a tent. But I wanted to test this, and so basically, if I wanted to use it as a tent, I laid down a ground sheet first, as you can see here, and then plunk the tent on top of that. So essentially, now you have a clean surface to work with inside if you want to use this as a tent. Now, just back this for a second here. This is a standard cot. This is one by Woods. You can get a Canadian Tire, and you can see the size of this thing. It's about 75 inches long. 75 inches long, and that will fit in there with room to spare. As I said, it's like 90 inches from one side. The bulge, you can see the bulge here. There's a similar bulge on each side. The tent is, or the cot is at a nice height where that'll actually fit in there, and you have about 6 inches of space between the end of the cot and the walls there. So that, again, this is why I recommended, or if anybody else wanted to do this, I would recommend make sure that you get a 3-person shelter, because the 2-person shelters are basically scaled down versions, and a cot like this will not fit in them. So here's the configuration, again, with a wide angle, with a cot and chair. And again, my purpose for this is, if I want to stay in a place at night, if it's a nice night and I don't need to have the computers out or anything like that, or even when I'm finished, but I don't feel like driving an hour or two back home. Like I said, this sets up literally in a couple of minutes, and boom, so does the cot. I can have a tent ready and sack out in a matter of just a few minutes. Throw a sleeping bag on that, and you're off to the races. So multi-purpose there. And I draw your attention to the windows here. Oops, I'll show you. Let me go back the other way here. These windows, as supplied, this is an ice fishing shelter, and as supplied, these windows come with this opaque cover, which just attaches to the top here with Velcro. It also has clear plastic windows, so if you want to be able to see out, but you don't want the wind howling in, these also attach and are completely removable. They just attach with Velcro. And I'll show you, this is the other, I'll mention the windows here again in a second, but this is the other thing that I want to mention. It's an ice fishing shelter, and it comes with these really heavy duty spikes that you can grind into the ice there to lock it down. And this is especially a good idea if you're anticipating winds where you are there. You don't want it to blow away on you. Obviously, I don't use these in the ground. Instead, I got these lovely spikes. They're about 10 inches long, very heavy duty. You can really slam them in with a hammer, and they will keep your tent in place for anything short of a tornado. As for the windows, this is the type of window that comes with it. As I say, you can peel it off. So basically what I did is I made 4 similar windows like this, but I made them out of screen. Just got the Velcro actually I think I got it at a dollar store. Cut the screening. It's just the plastic screening or the fiberglass screening that you use on windows, and just replicated the size, and voila, I've got windows that I can use in the summertime and let the air in and keep the bugs out. I also made this, which is a door. It's actually a screen door for the inside of the tent there. So when you're in there working, if you're in the summer there and it's a buggy area there, you can either close the main door that obviously comes with the shelter, or you can just attach this Velcro screen. So you've got a nice open space there, and again, you keep the bugs out. As I said, do-it-yourselfers. So I had occasion to test this up in the fall. I was up in northern Ontario, about 300 kilometers north of Sault Ste. Marie, doing some stuff out there for a number of days. And again, I was in a different location from night to night. I did some astronomy there, but it was more of a survey trip for some other work that I was doing. And I wanted something that was very quick to set up. It didn't take a lot of time. This is my chum's tent. He's got a more standard tent. And we had some pretty severe weather up there one night, where the winds really picked up, and it just, the rain just came down like crazy. And we actually wound up having to guide the tents down for the wind. And my chum actually wound up tying one of his guy wires to my tent because it wasn't going anywhere. So what I found is, with the driving rain, the seams at the top of the tent, after being pummeled for several hours by torrential rain, would actually start to admit a little bit of water. So I did this temporary tarp, and that kept it all out. when I got home, I figured, okay, if I'm going to use it for this purpose, I need to do a permanent shield on the outside, like a fly. So I built a fly just using a standard tarp here. And you can see the unusual shape of this thing. The fact that it's a cube actually made making a custom fitting tarp fly for this quite easy from a standard tarp.
Well, you got a minute or two left.
Okay, yeah, I'm almost done.
Okay.
Yep. So yeah, just a standard tarp there, and I just cut it where I needed to, and because it has the tent has these spikes coming out where you attach your lanyards if you want to really guy it down. I was able to attach the fly to that just using as you'll see in a second here, just using some clasps like that. So you don't have to tie it down, you just attach it to those spikes. If you need extra grommets, they're easy enough. You can get a grommet kit and put in extra grommets where you want them. And so that makes it quite easy. And at the ends, in the corners, I just attach from grommet to grommet with book rings there. And again, it keeps it a nice square size and makes it quite easy to use. Okay, so the last purpose I have for this is, and I had to fudge this slide because of COVID, is one of the things I found is that this shelter is very lightweight, but it's very strong. And unfortunately, you can't really grab it easily from the outside because the poles are all internal to it. But if you're out in the field with a chum and stuff like that, it's super easy to just pop this. Even if you're not using this thing for anything else, pop it open. And within a minute, you've got a shelter that you can easily lift over a sizable telescope and keep your telescope covered for the night, if that's what you want to do. So this is, again, my multi-purpose unit here. Makes for a nice instant shelter for your equipment when you've decided that it's time to sack out in your regular tent.
Okay.
Just a couple of images there to close up. These are images I took using this. This is probably the most brutal night. This was an eclipse 2 years ago. Unfortunately, this was missed in most of Ottawa because it got cloudy. As you can see, it was pretty raw here. It did open up in my area, but I couldn't get it from where I was in my house, so I had to go to the field. I used the shelter there, and I was able to catch this lunar eclipse there, which was really nice. But it was minus 24. And the wind was howling. It was there had been freezing rain just shortly before that. It was not a nice night, but again, very warm in the shelter, and it made imaging this event easy. And again, another reason, my trees prohibit me from getting a target that I wanted to catch for years. This is Antares, and the M4 globular cluster there. This is just at my tree level for my big observatory at home. And as a result, I've never been able to photograph it from my main observatory. I've got to go out in the field to catch this. And again, I was using the tent for that to be able to get several hours of good imaging on this. So this is Antares, and caught all the lovely reflection and emission nebulosity around this. Oh, one other application for that tent. It is, after all, an ice fishing tent, and so if you're into ice fishing, well, there's the fourth application for it. So
All right.
That's an interesting fish you got there.
it's a very interesting fish.
Well, thank you very much, Paul. That was great. I especially like the tent that just it tends to assemble itself within
It's lovely.
That's fantastic.
It's lovely. I've never seen one of these pop-ups that assembles so quickly.
Right.
Yeah.
Well, I'm going to turn this over now to Doug, and we'll spotlight Andrea. Hope I did that right.
Thanks, Jim. Just wanted to mention or reiterate that for your security, do not click on any web links that might appear in the chat or the question and answer windows. We're discouraging people from putting them in, and of course we're discouraging people from clicking on them. But I'm going to turn it right over to Andrea right away. Can you share your screen now? Yep.
Yes,
please
I
take it
hear
away.
you very well. Welcome, Andrea.
All right, I am going to start. I hope everybody is enjoying the evening. I found the presentations to be wonderful. I'm a relatively new member of the Ottawa Royal Astronomical Society, and I encourage anybody out there who might be interested to join. It's a very friendly group, and there's a lot of member benefits. So let me get the slideshow going. There is a lot to cover, and I'm going to move pretty quickly. I will be posting this presentation as well as some of the videos that I'm referencing. I will put them on the RASC Facebook page. So you have a lot more beautiful images of the sky in your social media feeds these days. The pandemic has brought about a resurgence in interest in astronomy. A lot of the images that you see, however, are done using normal photographic equipment that you might have at home, but there are two important techniques that will allow you as a backyard photographer, astronomer, to take images of the night sky. The secret is tracking and stacking. Tracking is what you do with a star tracker to track the motion of the stars. Stacking is what you do with the images to combine them to build on the images that you want to share. These two technologies are the reason that we can do backyard astrophotography. So what is a star tracker then? The key to astrophotography is to have long exposures. You want to expose your digital sensor to as much light as possible because we are trying to image very, very dim targets. Unfortunately, after about 20 to 30 seconds with most cameras, the stars in your image will move, and that will create star trails. Now, there is an aspect of photography where people do star trails, but for the purpose of this presentation, we want pinpoint stars. This is an image I took in my backyard. It's a 3-minute exposure. And as you can see, the foreground trees are very sharp, they're bright, and they're in focus. However, the sky is a mess. So in 3 minutes, all the stars that you look up in the sky to see have moved a significant amount. And obviously for astrophotography, we do not want star trails. This is an image that I took with a 50mm lens from the backyard. It is tracked. It is a 180-second exposure. So that's 3 minutes with a star tracker that will follow the movement of the stars, and then they stay as a pinpoint. I also took 10 of these photos. With 10 3-minute photos, I can use software, and most of the software is free, to stack these images. Stacking means that you're basically combining 10 images into one, and in the digital world, you are adding more and more and more data. So you have the data of 10 images in one photograph. So that is the magic of astrophotography. It is tracking and stacking. So what is a star tracker? This is a star tracker that I use. It is called the Skywatcher Star Adventurer. And there are other brands out there. There is an Iotron version. There is one called Move, Shoot, Move. But basically, they all do the same. They are motors that will track the movement of the sky. So let's say you have, before you go out and buy anything, you should first of all take a look at your current camera equipment. If you have a DSLR or a mirrorless camera that has a fully manual mode, then you can do astrophotography. You need to, though, have manual focus because autofocus won't work. You want manual aperture, which is how wide open your lens is, because you want maximum light. You also need to be able to manually set the exposure time. Obviously, if you're a photographer, all of these words that I'm using make a lot more sense. If you are not a photographer, you will probably have to review some of the basics of photography, like aperture and shutter speed, before you get into this. To manage your shutter speed, and your shutter speeds are going to be long. They want to be 60 seconds. They want to be 120 seconds. Most of you will need to purchase an intervalometer, and I'll show you what that is later, but it's a little gizmo you can get on Amazon. It allows you to program a series of exposures. And that's the trick, is you want to have a series of exposures while your camera is tracking the sky. Next, you need to look at your lens, because different lenses will have a different field of view. And this is totally not to scale, this diagram, but I wanted to get the point across that if you have a 35mm lens, and if you're a photographer, you know that that's pretty wide. With a 35mm lens and a wide field of view, you don't have to be quite so precise with your tracking because it's so wide. As you get closer to a 250mm lens, that's a much smaller field of view. You need to have much better tracking or your stars will trail. I have a telescope that has a 2000mm focal length. And for that kind of focal length, you need tracking precision. But most of you won't have to worry about that. This is an example of an image I shot from my backyard, and it is a single exposure with a Nikon DSLR. So it's a normal camera that a photographer might have at home. I have access to full manual mode. So I used a 10mm lens, very, very wide. I shot at f2.8, which is wide open to let the most light in. And I did 20 seconds, and I did a high ISO to capture more light. And it doesn't look too bad, but after 20 seconds, I couldn't go any further. I would get star trails. Now this image, again, is a single exposure, but it's a single exposure at 120 seconds. It's the same camera, same wide lens, same aperture. I lowered the ISO a bit, and you can see you can collect a lot more detail with 2 minutes. Something that a lot of people may not know when you see an image like this is that this is a blend. The sky, to do 120 seconds of the sky means the foreground will blur. And to get a sharp image of the foreground, the sky will blur. However, these images try to stay true to nature and be realistic representations by taking the same photo at the same location, at the same settings. I use all the same camera equipment. I just blended 2 different exposures. So you will need to blend, and you will need to have some knowledge of Photoshop if you're going to do tracked images with a foreground. This image doesn't have a foreground, so I didn't have to blend anything. It is with a 50mm lens, and it's the Orion constellation, and the 3 stars in the middle are Orion's belt. And you can see some of the red from Barnard's Loop, and you can see a little bit of red from the Horsehead Nebula. Now, at 50mm, you really cannot go past 5 seconds without having any star trails. So you do have to track. And in this case, I tracked for 60 seconds, and I did 10 of them. And once you have those 10 images, you go over and you find a program. It's called the Deep Sky Stacker. It's free, it's online. It's a little primitive, but it does what it needs to do. And it will, you throw your 10 images in, and it throws out one image that has all your data in one place. Okay, now this is the Andromeda Galaxy, and here we have gone really narrow. So 250mm, I used a telescope, but you could use a lens. And in this case, once again, you have to track, and I tracked for 60 seconds at an ISO of 1600. Once again, you can stack it in Deep Sky Stacker, and then you have to do a little bit of processing in Photoshop to brighten the midtones and increase the contrast. You're not editing, you're not creating weird colors, but you do need to take the data and what we call stretch it a bit. All right. So after you assess your existing equipment, you need to select your target. And it's important that you match your target to the field of view in your telescope. And there are lots of websites like Stellarium, and I'm going to take you actually to Telescopius, which is one of my favorite places. And I'm going to see if I am sharing the right thing. Hang on. Can you see Telescopius now?
Yep, that looks good.
All right. All right. So I'm going to type in, for example, M4, which is the lovely globular cluster that Paul just showed us. And here it is, the globular cluster. And what I like about this site is over on the left, it tells us all about the weather. Over on the right, it'll tell us when this object rises, when it transits, and when it sets. And then over here, I can put in my camera. You see, I have the D7000, and I've inputted some sensor data. And I can pick a 50mm lens, and that's what the field of view will be of this area called Rho Ophiuchi. If I decide to use my other telescope, here it is, 250mm, you can see how much we've zoomed in. So it's a very different field of view. And if I got out the really big telescope, and I've never actually done this, but it's 2000mm. Oops, we're really zoomed in. So this is a great site to plan and make sure you pick the right targets that are the right size. And I'm going to go back now to the presentation. So summer's coming up, Milky Way season. These are some of the best targets you can try starting with astrophotography. I already spoke about the Andromeda Galaxy. It's very big, very bright. The North American Nebula, also a very big target and very near a bright star, which is helpful to locate it in the sky. The Lagoon Nebula is a beautiful one, as is the Veil Nebula. All of these photos were taken with a DSLR, and all of these photos can be taken by you. You have to track, though, and stack to see these. These are targets for winter. Now, I'll confess that not all of these photos were taken with a DSLR. Some were taken with an astro camera. But again,
Andrea, you're not sharing your screen.
Yeah, Andrew,
Okay.
you're not showing your screen. Yeah.
Oh, sorry, I lost it. I was wondering, I didn't see the right thing.
We have a great image of you, but not.
Oh, no, you don't want me. You want to see these. Hang on. I got lost. Coming out of there. There we are. Okay. No, not from the beginning. Not from the beginning. Right here. Sorry. These are the summer targets. And again, North America Nebula, Andromeda, and the Veil Nebula at the bottom right. These are the winter targets. The Orion Nebula, it's a very big, very large, and it's a wonderful beginner target. The Horsehead Nebula is down there. It's also really easy target because it's next to this very bright star Alnitek. And some of these were taken with an astro camera, but the Heart Nebula, because again, it's very big, it's a wonderful target for a DSLR camera. All right, so here we are now we have decided on our target. We have a camera. We are now going to put together the star tracker, and I actually have a little video that I am going to share, and hopefully I'll be able to share it properly. The big key, though, with a star tracker is you can't just track anywhere. You need to track in accordance with the alignment of the North Star. So stars will turn and move around the North Star. So the axis of your star tracker must point to the North Star, which is Polaris. And as I think Dave mentioned earlier in the day, the way to find Polaris is to start with the Big Dipper and use the two pointer stars, Merak and Dubhe, and they will point to Polaris. All right, I am going to, hopefully this works. If you can't hear what I'm saying, please let me know.
We can't hear the audio, Andrea.
Yeah, yeah. All right, I gotta fix that then. I'm gonna stop the share. I might go to YouTube and share that one. Hang on a second. I was worried that would happen. I did lots of tests and it all worked in the test, but it's not working now.
Yeah, that's what happens.
Yeah, I even tested with my daughter. And
No
it worked.
worries. I'm sure we can ask, steal some of Jim's time.
Yeah, no, we have it here. All right, so we're going to, wait, pause. I got to share this screen here. It's not very long. It's only about 6 minutes. So I'm going to share this. Share. And I'm going to turn up the volume here. I'm going to turn up the volume in the Zoom. And hopefully you can hear it. Can you hear it? Hi, I'm on.
Yep, you got it.
Okay, good.
It is faint though. If you could turn up the volume somehow.
I'm going to go and try to do that.
It's a fairly solid one because you don't want it to move and blow in the wind. You will need to have, it's the larger screw, although the Star Adventurer comes with an adapter for smaller. This tripod has a level bubble on it, and I also purchased this inexpensive hammock off of Amazon. This is what I'm going to use to hold my intervalometer at some point. So you're out in the field, you make sure that your tripod is set up securely and you can see towards the north. This is the equatorial base. You will need this to do photography. This usually sometimes it's sold separately, so be careful when you order to make sure you get the equatorial base. You will have to adjust it for our latitude.
No, it's not working, Andrea.
Yeah, you've got no volume now.
Have we lost it?
Yeah,
All right, I'm going to.
we can hear you live, but we got a comment in the chat saying that you're sharing through your microphone rather than through the share itself.
All right, do we have them in the right ears? All right, can you hear me?
Can hear you loud and clear, yeah.
All right, I'm going to forget this. I'm going to post these videos on the Facebook page in any event. So we'll go back to the presentation. All
Yeah,
right.
put the link in the chat as well if you could, Andrea. That would I'll make sure that it's.
Oh, I will do that.
Yeah, thanks.
All right. So let's go see where we are. All right, I'm just going to share the right screen. Okay, there we go.
Looks good.
All right, back on track here. Oh, so the video was going to show you how to set up the star tracker, which is actually right behind me. I could probably point to a few things here. The most important thing is that this axis is where you will point towards the North Star. The Star Adventurer has a polar scope in it, and you can use it to find Polaris. Once you've done that, then you can set up your camera, point it where you want to point it, turn on the star tracker, because once you've found your target, you don't want to lose it. To be fair to people who are trying to do it with the Star Adventurer, finding your target can be one of the most challenging things, particularly with the DSLR, which can be a bit, some of the targets are pretty faint. So you may have to do quite a few test exposures, recenter, and that can be a bit of a process, which is why some people give up on the Star Adventurer and go and buy a computerized mount. But for some targets that have a really, really bright star nearby, it's pretty easy to line up with the star tracker. Now,
The other thing that people don't realize when they start doing astrophotography is that capturing the images is only part one. Part two is the stacking and then the processing. So a lot of the stacking software is free, but it will produce a picture which is very, very dark. And that's normal and that's to be expected. What you then need to do is import this image into Photoshop, or there's different programs out there, and we do a stretch and we brighten it up. And you're amazed, it's amazing when you brighten it up, all the detail that you can find hidden in the data. There are many, many tutorials online for image processing. It's an art, it's a science, it's quite technical, and it is a big learning curve, but it is worthwhile. You just got to go one step at a time. And so on that note, I am going to talk about further resources, because frankly, everything you need to know about astrophotography is on YouTube. These two YouTubers in particular are photographers first, so they came to astrophotography with cameras and lenses. So if you are already a photographer, you might really relate to the tutorials by these two gentlemen. Two other YouTubers that are very well known in the astro community is Trevor Jones, or Astro Backyard. He's a Canadian. He uses telescopes a lot, but he uses a DSLR camera for the most part. He has some astro cameras, and he's an urban astronomer, and that's what Jim is going to talk about next. Dylan O'Donnell, he's an Australian. He has very humorous videos, but he does a lot of processing, and he talks about a lot of the technology behind telescopes and astrophotography. After you have mastered your DSLR, you can go to the next step, and that is attaching your camera to a telescope. And the configuration in this image is my Nikon attached to a small telescope. It's 250 millimeters. And I kind of like the telescope a little bit better than lenses because they are designed for astrophotography. So they have a flatter field, there's less distortion in the corner. They're meant to be used at night. And this one in particular has a way to mount an auto guider. An auto guider is the camera that is sitting, it's a camera and scope that will help guide the tracker. So the tracker is tracking, it has a motor, but the auto guider will send a little message down to the mount to correct it. And the Star Adventurer Pro does have an auto guider port, so it can be used to auto guide. And then once you've done with that, you will move on to the next phase, which is an astro camera. You'll see it's the same telescope as before, but I've attached an astro camera, and I have it on a quite large equatorial mount. And by the time you get to this stage, you know you've got the bug quite badly and you're going down the rabbit hole for a long time. There is a second video that I also have here that I prepared, and I will put a link in, and it talks about this particular setup, but on the Star Adventurer. So how you would attach an auto guider, how you would mount a bit heavier telescope, because there is also a declination and counterweight bar for a bigger telescope. But you'll see more about that in the next video. And finally, you can use an iPhone, but mainly you use iPhones at the eyepiece. And so this was my first ever image. I don't know if you can hear this or not.
Yeah.
I can hear crickets because it was taken on a summer night.
I thought it might be Saturn itself.
Yeah, no, I love the fact that I could, I saw Saturn. It was beautiful. I put my iPhone up and we could hear the crickets. And that's all I have to say. Please go to the Ottawa Center Facebook page, and I will put all the Star Tracker videos there. I wouldn't have had time for them anyhow, it looks like. And thank you very much.
Well, thank you, Andrea. Yeah, you're under time too. If you could post the links to those great videos, that would be wonderful. Yeah, be wonderful.
I will add those.
Great.
Where do I put them, in the chat or? In the,
I think in the chat would be better.
All right, that's where I'll put them.
Yeah. Okay, so I'm going to turn it over to Jim our final presenter, right? Before we get into the star party at 9 o'clock in a half an hour. So Jim, please take it away.
Great. Thank you, Doug. I will share my screen. Give me a moment. Okay, here we go. So can everybody see that all right?
Yep, that's good. Yep.
Yeah, it's fine.
So good evening, everyone. For the next 30 minutes, I will be talking about the challenges associated with trying to be an amateur astronomer in a large city. By the end, I think you will agree that what at first would seem like a hopeless pursuit is in fact not. So let's start with an image that I captured using my cell phone, taken in my backyard just this past Tuesday night around 11 p.m. The first question that comes to mind is, this is supposed to be a nighttime picture. Shouldn't it be dark out? Unfortunately, for those of us who live in or near a large city, night is no longer dark. All of the many sources of outdoor lighting that exists in a city have resulted in a dome of light pollution that blots out the night sky. To understand just how badly light pollution affects astronomy activities, a sky darkness index has been created. John Bortle first presented his idea for a sky darkness index in the February 2001 issue of Sky and Telescope magazine. The scale takes his name and is based on 9 categories, each defined by what can and can't be seen in the night sky under those particular conditions. The scale is widely used now for evaluating and comparing different astronomy observing locations. Each of the 9 steps on the scale has been given a name. From excellent dark sky at Bortle 1 up to an inner city sky at Bortle 9. If you live in Bortle 8 to 9 conditions, there is very little that you can see in the sky with your naked eye. Moving out to the suburbs and Bortle 5 to 7 skies allows for the Milky Way to be observed and a few thousand stars. Go further afield to rural skies will provide you Bortle 3 to 4 skies, where you can see structure in the Milky Way and deep sky objects like galaxies, nebulae, and star clusters with your naked eye. Finally, if you are fortunate to find yourself under Bortle 1 to 2 skies, you are in for a treat. Imagine it being so dark that the Milky Way casts a shadow, and there are so many stars in the sky that you become lost. That is every astronomer's dream. The last thing to note about the Bortle scale is that it is also associated with something called the Naked Eye Limiting Magnitude, or NELM. This is a measure of how bright the dimmest star you can see is based on your conditions. It is another way of evaluating how dark your skies are. So this next slide will present to you a simulated view of the night sky that we can see later in the summer, sometime around mid-August. Under Bortle 2 skies, there are thousands of stars visible. The Milky Way is easily visible with lots of structure, and there are numerous deep sky objects visible. Now consider the same scene under Bortle 9 skies. Can you see the difference? Only Jupiter and Saturn and a few bright stars are visible. If you want to know more about where to find dark skies, there are lots of resources online. Maps of sky darkness, like the one shown here for Eastern Ontario, have been generated using data from satellites. Very clearly, you can see that where there are people, there is light pollution. Most of the city of Ottawa is Bortle 8 to 9. To find skies as dark as Bortle 2, you need to drive at least 90 minutes west. So for those of us who are not easily able to drive to a dark sky, do we just give up on astronomy as a hobby? Well, it would be a very short presentation if the answer to that question was yes. So clearly the answer is no.
A good one.
I've put together a list of objects that an amateur astronomer might be interested in observing, organized from the dimmest on the left to the brightest on the right. Even from Bortle 8 to 9 skies, a large number of these objects are observable using only a pair of binoculars or a telescope. They are all bright enough to see through the light pollution. There are some additional objects that are technically observable from an urban location, but the view is not very good. The objects are bright enough to see, but their details are lost in the haze. The final group of objects on the list are simply too faint to observe visually in the city. You will note, however, that I've put an asterisk beside those two last groups of objects. That is because there are some secret weapons that you can use to help make these otherwise unobservable objects observable. The first secret weapon is light pollution filters. These are relatively simple pieces of equipment that block man-made light, but allow the light of the object you are trying to observe through. They come in standard sizes and thread conveniently onto the end of your eyepiece or your camera. And there's some examples shown there on the right. So how do they work? Well, the photographs on the left show what the light spectrum looks like for the four main sources of light pollution: naturally occurring sky glow, classic sodium and mercury vapor streetlights, more modern LED lighting, and the moon. On the right are plots showing the light spectrum of two common types of observing target: bright emission nebulae and galaxies. When we compare on the same scale the brightness of the deep sky object, in this case the nebula shown in red in the middle plot, to the typical light pollution in a city shown in gray, it is clear that the nebula's light is simply overwhelmed by the light pollution. Adding a light pollution filter, shown in blue on this plot, dramatically reduces the amount of light pollution getting to the observer, thus improving the object's contrast. To give you an idea of what you can see at the eyepiece, I have a series of sketches here that I made in my backyard of the Orion Nebula using different light pollution filters. You can see that as I moved from no filter to progressively more aggressive light pollution filters, the amount of detail that I was able to see improved. I apologize for my sketching skills. They are not, well, they're not all that good, but you get the idea.
Better than mine.
So light pollution filters are probably looking pretty good right now, but unfortunately, they do not entirely solve the problem. There are many brands and types of filter available commercially, but ultimately you will be limited on what filter you can use based on your telescope. Filters, after all, block light, so the size of your telescope plays a role. Also, light pollution filters only work on emission nebula. There isn't a filter available, at least that I've found, and believe me, I've looked, that can improve your view of other objects like galaxies or star clusters. However, all of what I just said is true if we were only talking about visual observing. There is another secret weapon that can remove these limitations, and that's electronically assisted astronomy. Electronically assisted astronomy, or EAA, is essentially using an electronic device like a camera or night vision goggles to gather the light instead of your eyes. By using such a device, you eliminate many of the limitations of visual observing because the sensors we're talking about are much more sensitive than the human eye. They're able to see over a much wider range of wavelengths. Depending on the device you're using, some of them can produce a full color image instead of just a monochrome image. And if you pair these devices with firmware or software, it is possible to perform all sorts of processing of the data to enhance the image. So what does EAA look like? Well, we already saw earlier this evening what it looks like when you use a pair of night vision goggles or a light amplification device. But this photo here shows you what my setup looks like when I use cameras for doing EAA. Essentially, the camera takes the place of an eyepiece. It's the same interface, it's no different. Most of the modern cameras that are available today use a USB connection to your computer. Some of them will also connect to a wireless device that you can then connect to using your phone or a tablet, which is actually what I think Andrea uses for her astrophotography. Although options that simply use a video monitor are also available if you don't want to have to use a computer out in the field. There are many commercially available choices today at a wide range of prices. So that's good news for us. To give you a basic idea of what you can do with EAA, consider this simulated image of the Orion Nebula. This is what you might see visually through a telescope with a light pollution filter. The image is monochrome and lacking in detail. Now consider this view captured from my backyard using a typical color EAA camera and a light pollution filter. Much more detail is visible in the EAA image, and the colors help to provide a better understanding of what you're looking at. Oops, went a little bit too far there in the clicks, but if you stick around a little bit later tonight, you will see even more examples of what EAA can do in an urban sky. So now I'm sure many of you are asking how much all of this costs. Well, it is true that the bigger your secret weapon, the more money it costs. Fortunately, the market for filters and cameras has matured a lot in the last 5 years or so, and there are a broad range of choices available. Filters cost from as little as $50 used up to a crazy $1,000 each. But good filters are available in the $100 to $200 range new. Very capable cameras are available for $200 to $300 and go up to a couple of thousand for the fancy ones with giant cooled sensors. Before you do anything, my advice is to join a local astronomy club and start asking questions. You will be surprised at the amount of experience that is available to you, which can save you a lot of time and money. Also, you should start small, growing your skills and equipment gradually. It is often the case that newbies dive in and buy thousands of dollars of complicated gear and then get very quickly frustrated trying to figure out how to use it. Urban astronomy, when you are properly informed and outfitted, can be a very rewarding pursuit, and I hope that you will consider it in the future. Thank you very much. If you have any questions, I'll be happy to answer them.
Yeah, we got lots of time. If people want to ask questions verbally or through the chat, I'll make sure that Jim gets them.
Looks like I could have talked a little slower.
We're getting lots of good comments, you notice in the chat, right? Cool, wow. I thought it was great too, of course. Yeah, most of us do.
So,
I can ask a question, Jim.
Sure.
Can you do video through one-shot cameras? I mean, this is probably a no-brainer question, but what's the difference? I mean, can you simulate video with one-shot cameras? I'm thinking of dedicated astronomical cameras.
Sorry, when you say one shot, you mean one shot color?
Yeah, or one-shot black and white too, or a mono, I should say. Can you simulate the video?
I'm not sure I know what you mean. You mean like a commercial point and shoot kind of camera?
Yeah.
If the camera has a video mode,
yeah,
and then you can pipe that video into a computer, say, so you can then do something with it, then yeah, you can, for sure. For example, there's a piece of software from an Ottawa area programmer called Backyard EOS. And it was originally for Canon DSLRs, but I believe there's a Nikon version as well. And it allows the image data and control of the camera to be remote from a computer. And included in that is a live view of what your camera sees. So that is one way of getting in at the image data that your camera is able to collect. Now, it's going to be a bit more clumsy than if you buy a dedicated camera meant for EAA, but it certainly is possible.
In the chat, Gabriel mentions that you can do it with recent CMOS cameras. It's the CCD cameras that are too slow to do video.
Well, I wouldn't say that it's too slow. Like, for example, the analog video cameras that Mellencam still sells, like the Exterminator line, that's a CCD based sensor. It's a very sensitive sensor. The proprietary circuitry to amplify the signal and reduce noise. That was the state of the art, 6-7 years ago, before these low noise backlit CMOS sensors started to come onto the market and be affordable. It was all CCD. That was the only choice that you had. Now CMOS technology is starting to catch up, and it's more prevalent, largely because of the lower cost.
I have another question from George. Is it worthwhile to try putting up panels to block incoming light?
Yes and no. There's sort of two levels of light pollution that you have to deal with. There's the light pollution that is in your neighborhood, so your neighbor's porch light or the street light in front of your house. That affects your camera's ability or your eye's ability to see in a different way than just the glow of the background of the sky. Mostly, like if you're doing visual, the nearby light that's in your vicinity really affects your ability to get dark adapted. So even just a porch light off the corner of your eye, it's going to not allow your eyes to go to full dark adaptation. So that's a big deal. So putting up blinds or that's one of the reasons that people build observatories in the first place, is to block all of that extraneous light so that they can get dark adapted more quickly and to a deeper level and be able to observe better. And the same is true of if you're using a camera. Any stray light that gets into your telescope from nearby sources will affect the contrast of the image. So it is a good thing to block those nearby sources of light. But then the glow, the dome that's over a city, that's just the scatter of light that's going up into the sky scattered back at you from the air above, there's nothing you can do to block that other than to use a filter.
Francois asks, how much wide visual sight in your backyard, let's say to see a reasonably good sky?
I'm not sure I understand the question.
I looked at that one. I tried to understand it. I didn't understand it either.
Francois, if you want to rephrase it a bit.
No,
Maybe how much of the sky you can see.
how much I can see. So my backyard, I have my telescope positioned fairly close to the house. And I did that kind of on purpose because there's large trees in my neighborhood that block the view in certain directions. And so the best point to observe from was close to the house, which gives me most of the eastern half of the sky down to the height of my neighbor's house. So about 10 or 15 degrees from the horizon. So that it's about 80 degrees. So not quite half of the sky I can see. I can't quite see all of the north, but I can see very well to the south. And that is plenty, more than plenty. I know other people like Jim Sophia, he only has a narrow range of angles that he can see off of his balcony. And he's perfectly content. You just plan what it is you want to look at on a particular night based on the time of year and the direction you're looking.
I myself, I've got 60 degrees in the south and in the east, but I've got a good view of the zenith. So if I pick something like tonight, for example, the Whirlpool Galaxy, it's going to stay in reasonable wide, well, enough for me anyway, for probably about 2 hours or 3 hours, something like that. Good guess, though, that Francois does confirm that he was asking about trees.
Yeah, so that there's like 80-foot tall oak trees down my street. So any observing from the front yard is impossible. But luckily, all of the trees are in front yards. So my backyard backs onto my neighbor's backyard, and they have no trees in their backyards. So that gives me a fairly clear line of sight, which is, it's workable. There's some power lines and things, but it's pretty minor. The trees looking in certain directions are all far enough away that the line of sight's not bad.
Thanks.
Doug, can you unspotlight Andrea and spotlight Jim?
Okay.
I can probably even do that.
Yeah, maybe do that, Jim.
There. Aha.
There we go.
Thanks.
If there aren't any
I have a question, Jim.
Sure, go ahead.
So you had that tri-band filter, and I know we talked about it briefly, but how do you compare the performance of the tri-band when you're doing imaging versus just, say, an H-alpha filter at one band?
It really depends on the type of object you want to observe. A single band H-alpha filter is blocking more of the spectrum than the tri-band. So it is giving you a little bit of an edge on cutting out even more light pollution. But if the object you're trying to observe has a lot of oxygen-3 in it, like a planetary nebula, for example, you might actually get a better image with the tri-band filter. So it does depend a little bit on what kind of object you're trying to observe.
Okay.
Answers your question?
Yeah, I've got some new night vision on the way, so it'd be interesting to pair it with that.
Another question, Jim.
Sure.
What about looking through a window screen in the winter?
That won't work.
Okay.
The window screen. I don't know if I can find an image. So it so happens that if you put a thin line, like a wire, across your telescope, you get something called the diffraction spike. So that's the light diffracting around this wire, even if it's hair thin, will cause a spike on your stars or anything bright in the image. So now imagine that you have 1,000 wires from a screen across your field of view. You're going to have thousands of diffraction spikes, and it's going to really rob the image of contrast. And it also actually blocks a percentage of the light coming in. So you will not get a good image looking through a screen.
And a window, someone's
A glass window, if it's clean, you can, because there's every time light goes from air to glass or glass to air, it refracts, it changes direction. So you probably will find that you get a ghost image. I know that, Simon, you've looked out a window at the sun before, correct?
Correct. And there's a massive degradation. Massive. You know, you pay thousands of dollars for the optics in your telescope, and then you look through common or garden window glass. I was doing it the same way Chuck was. It was freezing cold, and I didn't want to go outside. It was a compromise, a huge compromise, but it would not be an observing method.
I got over my fear of holding the telescope out over the winter, right, and just running the cables into the basement. I think Jim does the same thing, basically.
Yeah.
And it's great. We had a question from John. What is the advantage or disadvantage between CMOS and CCD sensors, other than CMOS sensors are cheaper to produce?
So that's sort of an exercise. It's like a history lesson, really, because if you were to ask that question 10 years ago, the answer would be CCD is the only sensor that you should consider. It has way lower noise, way higher sensitivity, and it's the way to go. But that was 10 years ago. 5 years ago, the answer would be, well, it kind of depends on how much you want to spend and blah, 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 because they're starting to get a bit more comparable in performance. Now, I would say that even on a performance standpoint, not just cost, but on a performance standpoint, CMOS has, at least commercial cameras, CMOS has surpassed performance of CCD. And that is entirely driven by things like the cell phone market. And well, mostly the cell phone market. The need to make cheaper, high performance cameras pushed the sensor manufacturers towards CMOS because it's much cheaper to manufacture in mass quantities than CCD. So that's where the money was, that's where the research went, and that's why CCD has kind of gone to a dead end. It's still used in research grade observatories because you can still, if you invest enough money in it, you can still get a sensor that is outperforms a CMOS sensor. But for a commercial market, there's no way you can beat a CMOS for price. And so all this investment by Sony and other manufacturers went into CMOS. And that's why now they've got CMOS sensors up to where they are better than the CCD sensors that were in state-of-the-art EAA cameras 10 years ago, or even 5 years ago.
Most of the manufacturers are now discontinuing CCD production as well. Jim.
Good. Wow.
Yes, I've heard that the wafers, the base wafers, I think, that come out of the silicon manufacturers, they're not making them anymore. There's just not enough profit in it, they've all shifted over to supporting CMOS. So it is kind of, unless you're getting it custom made for an observatory, it's kind of a dying sensor.
We have one final question from Andrew. I'm not sure. Well, Andrew seems to be having some problems getting focus on his particular setup. He asks, any tips for connecting a DSLR to an older reflector telescope?
Yeah, the reflectors, like a Newtonian style reflector, is not necessarily meant to put a camera on. And the main issue is how much focus range you have on the scope. They're set up for visual use unless you buy a reflector that's specifically made for imaging. Most of them are set up so that the distance that you can achieve focus with an eyepiece works in conjunction with the focuser that you have. And then if you stick a camera on there, you have to focus in much farther than if you had an eyepiece, and there's just not enough room on the focuser. And so some people go so far as to move the primary mirror up in the tube, or move the, I guess that's the easiest thing, is to move your primary up. So that changes the focus distance out further so you can achieve focus with the camera. But that's the major issue with using a camera with like a Newtonian style reflector.
Yeah, I have a Newtonian astrograph myself, that's built in to the scope. But I've also seen videos, and just the other day I watched one which someone took all fairly elaborate, to be very elaborate process of doing exactly what Jim's talking about, moving the mirror up to achieve sufficient focal length.
Now, you may be lucky, and you're only out of focus by a little bit, like maybe you only need another centimeter of in focus. In that case, you might be able to retrofit the focuser. There are focusers, aftermarket focusers available that are shorter, that can give you that extra centimeter, and that could possibly solve the problem. But it's a common problem.
Another trick is you can't, Andrew, use a Barlow. You are then changing how much magnification you are getting, but that will move the optical train around, and you could reach focus that way as well.
Well, that's all the questions we have, both in the chat and what I can see. Sorry, what I can see in the chat and in the Q&A. So I'd like to turn it over to Dave now, who will run our star party. Thanks, Jim.
Okay. Thank you, Doug. And so I'm not sure, are we going in the order that we have on our schedule here, folks? Is that the plan? So if that's the case, Jim, you're up first.
All right.
And are we doing cloudy sky or clear sky?
Well, let's just take a look, shall we, at the satellite footage here. This is what the skies look like currently in the Ottawa area. Those blue blobs are rain showers, and the white stuff is cloud. So I think the answer to that question is we will be doing the cloudy schedule tonight.
Which blue blob is Andrea? She said it's raining in Canada.
Well, Canada would be around here. So this is behind by a few minutes, but Canada is right here.
I just had to
Hey,
take
way
a
to
few
go,
takes
Andrew.
in. It was definitely raining pretty hard. So
Jim, I'm in the dome here, and I do have some clear areas of the sky, so we'll see what happens. I may be able to pull in some live images here.
Okay, well,
Jim, I'm about 20 kilometers west of Almont, and my sky is starting to clear out here. I've got some pretty big gaps up here.
okay, well, let's say that if when it's your turn to present, if you have clear skies, you can show something live. If you have cloudy skies, then you can pretend that you have something live, but in reality, it's recorded.
Gives the audience a pretty realistic idea of what conditions can do, eh?
Yes.
Jim, in that case, maybe we could sort of ask people that think that they can go live to sort of give us a heads up when they think they've got something, and we can give them priority before a cloud comes in and obscures it. And
Yes.
the rest of us that are going to be showing archived images, we can take it one at a time.
Okay, sounds like a plan. So who's got a sucker hole open right now?
Haven't got an alignment yet, guys. It's not quite dark enough here, but I'll be a little bit.
Okay, well, we'll stand by, Lance.
Okay.
Yeah, I can go ahead and start things off if we like. So I will share. This is an image of an object that I captured using my EAA setup from my backyard last spring, so about a year ago. And this is of the galaxy M87. It's in the constellation Virgo. It is a super giant elliptical galaxy with about a trillion or several trillion stars in it. So it's a massive galaxy. And it's roughly spherical in shape. It is one of the most massive galaxies that we know in the local universe. It has a supermassive black hole at its center, weighing in at about 2.4 billion solar masses. It is actively ingesting dust and gas, resulting in a long jet of energized material coming out from the black hole. And you can actually see that jet in my image. If I zoom in here, you can see the jet there sort of at the 2 o'clock position. So that is a stream of energized particles and photons, all kinds of different types of radiation, rocketing away from this massive black hole in the center of this galaxy. By the way, this black hole is the same one that we were talking about earlier today during the question and answer period. It was imaged directly using the Event Horizon Telescope back in 2019, which was, to be frank, quite an astonishing feat, in my opinion. A telescope essentially the size of the Earth used to capture an actual image of a black hole. So that's pretty cool. All right. Who's next?
I'm happy to go next. What I want to do here. We were talking earlier about the size of telescopes, and one of the things that I've been turned on to very recently is getting smaller and smaller telescopes rather than larger and larger. And I must admit, I caught this fever here from Jim. Usually it goes the other way around. You get into a telescope and think, well, what if I had an even bigger one? This telescope here, you can see this is my computer mouse. That gives you an idea of how big this telescope is. That's the telescope. And then I put a really small camera in there. That's the smallest camera I have. This is the smallest telescope I have. Its diameter is 50 millimeters. That's 2 inches. And as I believe it was Attila pointed out, smaller telescopes like this give you a really wide field of view. And that's what I really want to show you. What I want to show you is this image. Oh, am I showing you this? Yes, I am. I am sharing. Good. This image here comes from the Milky Way. Of course, we can't see this. This is what you'd see. We think this is what the Milky Way would look like if you were on the outside looking in. And the idea is that there are these arms, and this cluster of stars here is somewhere in one of these arms. We won't worry about which one it is. But the thing is, this is looking right into the Milky Way. And there are literally in this field of view, I don't know, maybe there's 1 million stars in here. This cluster here is so big that most people, when they're looking through your average amateur telescope, are probably looking at something like this. So you don't really get to appreciate what it is you're looking at until you can see the outside of one of these really large clusters. By the way, I just scanned over this thing here. That is a dark nebula, which is actually a large cloud of opaque dust. There are stars behind it. There are stars on either side of it. It's in front of this collection of stars, and it's blocking the light, which is why we can see it. But the point is that this is called the Scutum star cloud. It's also called M24, for those of you that like these things. It's part of Messier's collection. The density of stars here is in such stark contrast to the much lower density of stars out here. And this does reflect a real change in density. This is in the arm, and this is getting out towards the exterior of this galaxy arm. This, by the way, just if you're interested in a few details here, this thing is about 9,500 light years away. In other words, the light from this cluster of stars took 9,500 years to get to us. So whatever is actually happening around any of the stars here actually happened 9,500 years ago. Notice, though, that within this cluster, there are all kinds of details you can see when you see the big picture. You see an even greater density of stars here. So you've got a cluster within a cluster, and then you've overlaid a dark cloud of opaque dust on top of it. So that I'll leave it at that for now in case somebody else has something else to come up with. I've got 3 more of these large wide fields of view to show you. By the way, these were taken from my backyard in downtown Ottawa. So as Jim was pointing out, urban astronomy can be extremely exciting, and it can show you enormous vistas on the sky overhead. I'll stop the share there.
I have M13 to share, if that's okay.
Yep, not a problem.
Okay.
Just give me a second here.
All right.
There, now you're spotlighted.
Okay. I thought I had the image. Oh, wait a minute. Sorry about that. Okay. Oh. All right. I seem to have lost.
I can go ahead if you want, Jim, while you look.
Yeah, I'm just trying. I know I'm right here. It's funny, I can't see it over there. That's weird.
Why don't I'll pop on with mine, and then
Okay, go ahead.
and then we'll come back to you. So I'm going to
Sure.
share an image that I took over Easter. And let's see if I can, there we go. This is M51, the Whirlpool Galaxy. And this is actually 2 galaxies that are colliding with each other. There is a small little yellow galaxy, and then there's a much bigger main galaxy. And this is a sort of an interstellar collision. And what has happened when these 2 galaxies collide is that there is an explosion of star formation. There are dust lanes, and there's all kinds of colors that happen in this galaxy. So when people look at this galaxy and they say, why is it really that colorful? Well, if we looked at it with our eyes through a telescope, it might be very much just a white smudge. However, the camera sensors are able to pick up the blue color comes from a star forming regions where there are young stars that are just being born. The red areas are actually areas of hydrogen emission. And then the yellow core of M51, that is the older stars are in yellow. And you can see that as a result of this collision, there are waves of dust that are being projected out across the universe. And essentially, this is a beautiful spiral galaxy. I should mention this is a pretty easy one to find as well. It is in the constellation is Canis Venatici, but it's very close to the Big Dipper. So if you know the Big Dipper, there is a handle. This galaxy can be found right near the handle. So it is visible to us in Canada for a good part of the winter. This galaxy was shot from my backyard and using my larger telescope, which is an 11-inch Schmidt-Cassegrain, but I used it in the hyperstar mode. And the focal length is about 540 millimeters. And that is basically the focal length of a telephoto lens. It's not the biggest target, so when you see here, I've zoomed in quite a bit, but it is a very bright target. It's very easy to find in a small telescope, and it has been mesmerizing astronomers and scientists for centuries. That is M51, the Whirlpool Galaxy.
Okay, I would like to give another try to M13. Share my screen. Here we go. Can everyone see M13?
Yep.
Okay. Great. It's called the Great Globular Cluster in Hercules, and it's one of my favorite objects to look through. Not only to image it, but also to see it through an eyepiece. Memorable experience being in Foymount and looking at M13 through my 18-inch Dob through a nice eyepiece. It was quite nice. And so this is several 100,000 stars that are gravitationally bound together in the constellation Hercules. And it's the prominent globular cluster in the Northern Hemisphere. M13 was discovered by Edmund Halley in 1714 and cataloged by Charles Messier in 1764. M13 has a diameter of approximately 145 light years. It's approximately 22,000 light years from Earth. What I've read is that globular clusters in spiral galaxies are most found in the galactic halo. They tend to be older, more massive, denser collections with fewer, heavier elements than the open star clusters, which are generally found in disks of spiral galaxies. Apparently, there are over 150 known globular clusters in the Milky Way. Thank you.
Okay, who would like to step up next?
I've got a follow-on from Jim's, which would be very appropriate. If
Okay.
I can, there we go. It's this one. This is also, let me bring this up larger. I just realized I didn't do that last time. There we go. As Jim pointed out, there's a sort of side view of a galaxy with globular clusters in a collection around the outside. They also occur inside, but the main ones occur outside. The reason I really like this image, and again, it was taken with my 2-inch telescope, is here is an open cluster. Sorry, a rather diffuse globular cluster. It's called M38. But the reason I like this image is this image, this object here. It's also a globular cluster. Well, just for the sake of argument, assume that this one is the same size as this one. Then that would mean that this one is further away. We know that space is three-dimensional, but we're so often looking at things and thinking that these stars, for example, are next to each other, or that this bright star is next to these stars over here. Whereas it could be that this star is much, much closer if it's the same size as these stars, or it might just be a really big star. But as I say, if we assume that this cluster and this cluster are about the same size, then it turns out that this is a lot further away. And in fact, when you look at the numbers, it turns out that this is the case. And my point here is that when you're looking through even a small telescope with a wide field of view, you get this perspective. In this case, I think you get this three-dimensional perspective, which we don't always get depending on where we're looking at in the sky. So I really like this image for that reason. You also can clearly see, of course, the environment around this cluster. With your average 10-inch telescope, you're actually ending up looking at this, which means you're looking even inside this cluster and not really seeing the environment that it sits in. One of the joys of a small telescope. The other joy of a small telescope, of course, is cost. They cost a lot less. You're talking hundreds of dollars rather than thousands of dollars. But that's an aside. That's what I have to say about M38.
Can go next there, guys, if you'd like.
Sure. Oops, just a second here.
This is live, Lance?
No, I've got an alignment though, but still
okay.
Just waiting for it to get a little darker.
Okay.
Can you see my screen there, guys?
Oh, yeah.
Yeah, okay. So, yeah, I've got Messier 27, or the Dumbbell Nebula. And this is a planetary nebula. Distance, it's within our own region of the Milky Way galaxy. So by cosmic standards, pretty close to us, only about 1,700 light years away. My understanding was that when these planetary nebulas were first discovered with the more primitive telescopes at that time, they knew what our planets looked like, and these objects looked similar to planets in those telescopes. So they were given the name planetary nebula, sort of a misnomer, though. They're actually the remains or the formed by the process of stars shedding their atmospheres near the ends of their lives. These are some images I took of M27 using a Malincam DS10C camera last fall. I was using a technique where we start off with low exposures and gradually use a live stacking process to accumulate data and gradually increase the exposures. So this image here was starting off at 5 seconds. There was 10 stacks there. And you'll see it there'll be more data here as we go along. This is 21 stacks up to an exposure of 6 seconds, 31 stacks at 7 seconds. And you can see it starting to build there. 40 stacks here with the exposures up to 8 seconds, 50 stacks up to 9 seconds. And we go along, and it gets really interesting when you get to this stage. You start to see these other lobes here to the side. So that's up to a 14-second exposure. And I think that's the final one there, up to 18 seconds with, it was like 100 stacks there. So yeah, M27, commonly known as the Dumbbell Nebula, the first planetary nebula ever discovered. Probably the finest in the sky, arguably. It's probably one of the largest and the most detail. Easily seen in binoculars and a popular observing target for amateur telescopes. Charles Messier discovered the object in 1764. He described it as an oval nebula without stars. William Herschel invented the name planetary nebula for this class of objects around 1784. He found them to resemble his newly discovered planet Uranus. The name dumbbell goes back to William's son, John Herschel, who compared M27 to a double-headed shot. This planetary nebula is certainly the most impressive object of its kind in the sky, but at visual magnitude 7.4, it is only the second brightest. While the Helix Nebula in Aquarius, which we may have a look at later, is slightly brighter at magnitude 7.3, it has a much lower surface brightness because of its much larger size. So with the Dumbbell Nebula here, the two bright triangular lobes that give rise to the dumbbell's name extend north and south to an overall length of 8 minutes by 6 minutes in the sky, and a faint halo extends out over 15 minutes, half the apparent diameter of the moon. Several stars are superimposed on the nebula, the most conspicuous in the center of the northern lobe there. Like many nearby planetary nebula, contains knots. The central region is marked by a pattern of dark and bright cusp knots and their associated dark tails. The knots vary in appearance and form symmetric objects with tails to rather irregular tailless objects. So a lot of detail in the center of the nebula there. Zoom in here. The central star of M27, just visible at magnitude 13.5, is surrounded by a slightly darker area. It has a faint magnitude 17 yellow companion 6.5 arc seconds away. And about 2 degrees west of M27 is an inconspicuous open cluster, which contains about 20 to 30 widely scattered stars. So yeah, definitely a really interesting object, probably one of the finest objects in the sky as far as color and detail that we can see. Always a great object to show at something like this or at public outreach events. We see it from its equatorial plane, similar to another planetary M76 in Perseus called the Little Dumbbell. Viewed from the poles, M27 would probably appear ring-shaped, similar to the Ring Nebula. So it's mainly because of the angle that we're looking at it that gives it this appearance. They're not, that distance I gave you was sort of an estimate. We're not 100% sure, and the age is also uncertain. By one estimate, the bright portion of the nebula is expanding at a rate of 6.8 arc seconds per century, leading to an age of about 3,000 to 4,000 years. By another, they're giving it a range up to 15,000 years. Spectroscopic observations indicate the nebula has an expansion velocity of 31 kilometers per second. So unbelievable that these things are expanding at that kind of a rate, but we'll never notice the difference. They're just so large. The physical radius is about 1 light year. So yeah, that's a great object, the Dumbbell Nebula.
Dave, I can jump in next if you want.
Lance, it's worth pointing out that something like the dumbbell is also the kind of object which we'll often use to make sure that our systems are calibrated at the beginning of an observing evening.
Right.
So Paul, you go ahead, or you can go share your screen.
Yep. You seeing that?
Oh, yep, now we do. Yeah.
All right. I'm going to show you one of my favorite regions in the sky, especially in the summer. Yeah, when it's not freezing cold out. This is just an awesome region to explore, even with binoculars there, and actually especially with binoculars if you're under a dark sky there, because it's loaded with Messier objects and a lot of structural stuff in the Milky Way itself. This is looking almost towards the center of our own galaxy. Of course, we can't see into the center because of the numerous dust clouds you can see here that lie between us and the actual center of our galaxy. So these are dust clouds from the nearest spiral arm heading in towards the center. And you can see there's a lot of there's a lot of interesting nebulosity, including the dark horse here. You can see the dark horse running sort of up this direction. I won't talk about this really bright guy because I think Jim may have something to that effect. But my interest is, or the one I wanted to show you is this guy here, which is the Terrific Nebula. Again, it's just one of many lovely objects in this area. This particular view I shot with just a 70mm lens, so fairly nice wide angle on this. And just with a Canon 60DA, the whole assembly was on a Skytrack there, or rather a Star Adventure mount. And it's actually a stacked image. I used 35 90-second exposures to stack this, so that really reduces the noise, and it certainly helps to bring out a lot of the detail. I've got a few views of this, just getting a little bit closer, because this is, as I say, a fairly wide angle there. This is a little bit closer there, and again, this is the lagoon there, but I won't talk about that. The Terrific up here, this is, you can start to see a bit more detail in it now. This is actually kind of cool because just even in this view, you've got three Messier objects. You've got M8, the lagoon, you've got M20, the Terrific, and you've got M21, which is a nice cluster right in there. So the Terrific itself is, it's a combination. You can see the two striking differences in colors there. It's actually a combination of reflection and emission nebulosity, and we believe it's about 5,200 light years from us here. I'll get a little bit closer there. You can see the Terrific there, the blue reflection nebula here, and the emission nebula in red here. The nebula itself is about 21 light years in diameter, give or take. And again, you've got M21 up here. So just a lovely view there. And again, under a dark sky there, you can really see a lot of definition in the actual dust clouds of the Milky Way, including some of those very dark ones, the dark lanes that you see there. And my final view, just again, a little bit closer there. This is an area where new stars are forming. For those that aren't familiar with this concept, the reflection nebula is just like it sounds. It acts like a big mirror reflecting starlight from some of the brighter stars in the vicinity, whereas an emission nebula actually absorbs the energy of that starlight and then re-emits it at the longer red wavelengths. So that is the Terrific Nebula, and it's coming up to that point in time where that whole region, the M20 and M8 region, is going to be beautifully placed in our southern skies under some warm summer nights. So I hope you get a chance to get out and enjoy that. Thank you.
Yeah, Paul,
yes.
Paul, I wanted to ask how you got the blue wavelength so well.
Really, it results from the fact that you can stack these images, and the blue is much fainter than the red. So you've got to stack a lot of images, and then it's processing from there. You can use your processing to differentially boost the blue wavelengths, the blue colors in there by using appropriate masking and something like Photoshop to bring them out. The information is always there. It's just a lot weaker than things like the red, and you've really got to push it, especially since the cameras themselves are typically weaker in the red, and that applies to CMOS as well as CCD cameras. Those sensors are typically preferentially more sensitive, in fact, by a large margin usually in the redder wavelengths than they are in the blue. So if you get enough data, you stack it, and then you can stretch the blues to bring out that information.
Yeah, that's a
Okay, thank you, Paul.
You're welcome.
I have another one if no one else.
Okay, just a sec here. There you go, Jim.
Okay, let's hope this works. All right. So this is very familiar. Another favorite object that we see quite often. This is M57, the Ring Nebula. And it's a planetary nebula. And as you know, it's a star at the end of its life. It's shedding its gas and leaving behind a white dwarf. And my question to the audience is, if we just look very closely, I'd like to know, where is this the white dwarf, or is that the white dwarf? I would think that is, but I see two stars in there. In any case, I'll just, throw that out. Some facts about the Ring Nebula. It's ejected its outer layers approximately 6,000 to 8,000 years ago, and they've since expanded over an area of 1.3 light years in radius. The nebula is expanding at a rate of about 1 arcsecond per century, which corresponds to a velocity of 20 to 30 kilometers a second. The deep blue color in the center represents helium, from what I've read. The light blue color in the inner ring is a glow of hydrogen and oxygen, and the reddish color on the outer ring is of nitrogen and sulfur. It lies approximately at a distance of 2,300 light years from Earth. Thank you.
Who'd like to go next?
Yeah, I have something I can share.
Okay.
So just to back up for a moment, most of the images that I'm sharing tonight, at least the images of smaller objects like galaxies, were taken with this setup. So the 10-inch Ritchie-Chrétien telescope with a monochrome Malan camera, a DS432. So I use both monochrome, and the red camera in the background is a one-shot color camera, an ASI 294. So you'll see images captured with both of these cameras, and both with the 10-inch telescope and then various smaller refractors. So the image I was going to share is this one, which at first glance, you don't really see much, but if you look carefully, you can see a very faint, what looks like a cluster of stars, but in fact is a galaxy. So this faint grouping of stars that I'm circling in orange is what is known as a dwarf galaxy. So it's a very small galaxy with only a few million stars. And these galaxies are of interest because it's believed that these smaller galaxies act like building blocks for larger galaxies. So this dwarf galaxy is actually orbiting the Milky Way. It's located in the constellation Leo. The bright diffraction spikes that you see at the bottom of the image, that's from the star Regulus, which is the brightest star in the constellation Leo. It's very, very close to it, which actually makes it difficult to observe this object because its light is spread out over a large area, making it diffuse and difficult to see. So scientists think that this small galaxy is about 820,000 light years away, which sounds like a lot, but in the universe schemes, it's actually quite close. So it's orbiting our galaxy. It's a member of our local group, but it's thought to be one of the more distant of the galaxies that orbit ours. There's a number of these spheroidal dwarf galaxies orbiting our galaxy, over time eventually getting gobbled up by our larger galaxy's mass. It's also thought to be relatively young because most of the stars in this galaxy have what's called a low metallicity. So that's a measure of how many of the elements in the star are heavier in mass than hydrogen and helium, which are the main two building blocks that stars start from. So if a star has gone through many generations, it will accumulate over time more and more quantities of elements heavier than hydrogen and helium. And this can be measured using spectrometers. So the stars in this particular galaxy don't have a lot of material heavier than helium or hydrogen, which suggests that it's a fairly young galaxy. The stars in it are young, like first or second generation. Now, there's also not a lot of new stars being formed in this galaxy. And from what scientists can figure out, it's because all of the gas and dust that used to be available to make new stars was vacuum cleaned out of the galaxy by the Milky Way. The last time this galaxy passed close to our galaxy in its orbit, they believe that our galaxy's larger mass was able to pull all of the dust and gas that was freely available out of this galaxy and added it to our own. So it's sort of a dead galaxy, not much new going on, but perhaps someday it will spiral in and eventually combine with our galaxy. So that's Leo 1.
Okay, thank you, Jim. I've got Andrea. You're muted, Andrea.
I am muted. I'm unmuted now. I'm going to share. So like Jim, I was looking to show you, I'm going to show you quickly what telescope I'm using. Where's my Zoom? Okay. Share the screen. So my images are mostly done using a Schmidt-Cassegrain telescope, but I'm not using it sort of straight through the telescope the way you normally would look through the telescope. I'm using this setup, which has, it looks really strange, but it has a hyperstar, which is a reducer lens that actually goes on the front of my telescope. So even though this telescope has almost 3,000 millimeters of focal length, I'm not imaging at 3,000 millimeters of focal length. I use the hyperstar, and you'll see there's a red circular thing. Then that is my camera. So that's the camera that I use for my images, particularly of galaxies. Okay, move forward. There we go. And that is what I use to take a picture of this galaxy. This is Messier 101. It's also known as the pinwheel galaxy for obvious reasons. It's a beautiful pinwheel spiral face-on galaxy. It is actually a huge galaxy. It's very, very big, very hundreds of thousands of light years across. That actually makes it beautiful to take pictures of, but it makes it very difficult to see visually because its brightness is spread over a wider area. This image was taken again with the hyperstar, and I would stack, I would take about 3 hours of 3-minute exposures. So I would take 3-minute exposures, I would do that for approximately 3 hours, and then I would stack all of those images. I use a color camera. Some people use monochromatic cameras, but I don't. I have, it's called a one-shot color camera. So these are colors that are coming into the camera sensor. There's blues, there is reds, and the central core is yellow. So part of the challenge of galaxies is once the data comes in, you want to work to extract the colors. You're not inventing them, you're not colorizing them, but your sensor is receiving different wavelengths which represent an actual true color. And so we try to represent those in the most accurate way. And I wasn't so good at this, but lots of people will collect, try to bring out the red in the spiral arms, and the red represents nebulas, but from a different galaxy than our own. So that's all I have to say. Oh, this one actually is near the Big Dipper as well. It's basically across the way from the last galaxy I showed you. So a very popular target for photography. and easy to see in our Canadian skies. That's all I have to say about M101.
Okay, thank you. Who would like to go next?
I have something set up for you.
Okay.
Going back to being in the interior of our own galaxy, sometimes some of the things that you can see in the sky are so obvious, you wonder if this is coincidence, or somebody drew it this way, or is it just that we, with our eyes and our ability to recognize shapes, say, I know what that looks like. Well, this here is an image that I took again from my backyard of what is called the North American Nebula. This was taken with this black and white image was taken with my 2-inch telescope with that very small camera that I showed you earlier. And this was taken at another site using a telescope which was 4 times the diameter, but with a much, much larger camera, which therefore was able to actually capture a bigger picture. And I think you can see that this thing really does look like North America. This looks like Middle America, Central America. There's the Gulf of Mexico. Oh, sorry, the Gulf of, Mexico, Florida. This would be the United States with all those Americans and all their lights and what have you. And we would be up here in Canada. Well, what I took with my 2-inch telescope, you can see I'm in the lower part of the United States, so to speak. There's Florida. Here, of course, is Central America. But forget all that. It just looks like it, but it's called the North American Nebula. And what it is a collection of stars and gas. The stars are being born from the gas. It's a huge nursery of stars. But what's fascinating is that in the area of Florida and Louisiana, let's just use those terms for geographical facility, you can see these, as Paul pointed out to us, you can see these dark trails in here. This again, of course, is corridors of opaque dust, which is obscuring the brighter gas and the stars behind. But down here in the Central American portion, you see these very bright curves here, discrete. And what these are pressure fronts. Not sure why, but something is pushing up from this away into this gas and is compressing it. And as you compress gas, so it gets warmer. This is basically the same principle as fridges and rain, for those of you know about these things. So this again is a pressure front. The gas here is ramming into this gas here, and this is the front, which is glowing brighter. But the remarkable thing is all the stars that you can see being born in here, all of these details within the gas, this cone-like structure here, I'm not sure what's causing that. I don't know if it's something pushing out this way or something pushing in this way, but there's clearly some kind of a movement vector in this direction here. It's amazing. A 2-inch telescope, a very small black and white camera, and you can see all these details. Now, I have to confess, there's something rather special about this little camera that I'm using. It's a Mallancam camera. It has a very, very small chip, which is why the field of view is smaller than in this case here, but it is brutally sensitive. And it is able to pick up all kinds of details like this for such a small camera. So bottom line here is you don't need to spend huge amounts of money. You don't need to buy big cameras. You don't need to buy big telescopes. I love them, by the way, both big cameras and big telescopes. And I also have to confess that the small telescope, it had to be guided. Something had to be carrying it. So in fact, I stick my small telescope on my big telescope and then take the wide field picture. Mind you, at the same time with another camera, at the very same time, I'm looking through the bigger telescope at probably more details, like, for example, an area like this. Just another trick of what one can do with urban astronomy.
So, Simon, we have a question here.
Yes.
I don't know whether you'd be able to answer. What is the dust made of?
Oh, the dust essentially is what has been blown out. Well, let me start again. The dust that we're looking at, we do know what that dust is. That dust is made of the most primitive early parts of the dust are made of a calcium silicate. Most rocks that you will see, if you go into your backyard and you pick up a rock, or if you go and pick up a piece of granite, it's actually a silicate. It's made of silicon and oxygen, plus a little bit of iron, a little bit of magnesium, a little bit of calcium. If you live in Ottawa, it's a different question. The rocks that you see around Ottawa, most of those are actually limestone, and that is a calcium carbonate. But if you go up into the Gatineau Park, most of those rocks up in Gatineau Park, they're part of the Canadian Shield, and most of that is silicate. So calcium silicate. This is what the very early stuff was made of. As the dust cloud evolves, as you start to make solar systems and you start to make stars, that dust will then be made of other silicates, which probably have iron and magnesium in them. But essentially, silica and oxygen are your major components.
Okay, thank you very much. And the response to that answer is wow, with 3 exclamation marks. Thank you, Simon. Okay, who would like to go next?
I guess I can pop in with another picture of a galaxy.
There you go.
All right. So the reason I'm focusing on galaxies, at least initially, is because springtime is a great time of year to observe galaxies. It just happens that at nighttime, this time of the year, the Earth's night side is facing out of our galaxy. So we're looking away from the disk of our galaxy out into intergalactic space, and with fewer stars in our way, we can see more of the galaxies around us. So this is a group of galaxies that is also in Ursa Major, not that far away from M51. And it's sort of a 3 deal here. We've got a large spiral galaxy, NGC 3718, but it's quite distorted. It's not what a normal spiral galaxy looks like. The arms are all stretched out, and the core is kind of got a weird shape to it. And the reason for that is the neighboring galaxy, NGC 3729, is interacting with it. So these 2 galaxies have had a close flyby sometime in the past. And as a result, the spiral arms of the larger galaxy have been all distorted. The stars have been all stretched out, and the original shape of the galaxy has been lost. In addition to that, you can see in the smaller galaxy, 3729, there's a bright ring shape. That is actually regions of vigorous star formation. So one of the side effects of galaxies interacting with each other is it can cause a lot more star formation to occur. The effects of the gravity of one galaxy on another, moving stars around, causing shock waves in the clouds of dust and gas, can trigger more vigorous star formation. And so this bright ring we see is all new stars being formed, triggered by the interaction between these 2 galaxies. So these 2 galaxies, they are fairly far away. They're about 57 million light years away. But interestingly, the group of galaxies that are in the upper part of the image that I've labeled A, B, C, D, E.
Hey, Kirsty, you call?
Your mic's on, Dave. These 5 galaxies are part of a close galaxy group called Hickson 56. Hickson was an astronomer who searched through photographic plates, I believe taken at Palomar. I'm not sure on that, but he put together a catalog of these clusters of galaxies that are fairly closely packed, and he just numbered them sequentially. So this is number 56. Now, what's interesting about this cluster of galaxies is that it's estimated to be about 400 million light years away. So almost 10 times as far away from Earth as the two galaxies in the foreground. So it's, from that perspective, kind of an interesting extension of Simon's image of the two star clusters, where you have something quite a bit further away in the background compared to what's in the foreground. Kind of an interesting perspective. And then all of the stars that we see are all in our galaxy, you know, only thousands to tens of thousands of light years away, as opposed to tens of millions like the galaxies. So yeah, that's it. Thank you.
Okay, thank you.
Oh,
Go ahead, Paul.
I was just going to say I can jump in if you want.
Okay, sure, no problem. Sorry for the interruption there, Jim. I didn't realize I was not muted, and I think I just tried to talk to Chris, try to coordinate things as we transfer things over here. So go ahead, Paul. I can't highlight you because you don't have your video on, so go ahead.
Okay, no problem. Oops, got the wrong one, sorry.
Nice desktop.
Let's see if I can get the right screen this time. There we go. How's that? Are you seeing that?
Yep.
Okay. So this is one of my favorite nebulas photographically. Visually through a telescope, I've seen this through a number of different telescopes, and it's certainly not as interesting visually as it is photographically. At least that's my impression of it. That the details aren't nearly as apparent, but photographically, this thing really pops out. This is Messier 16, the Eagle Nebula, and you can see at the center of this image the well-known pillars of creation that Hubble did such a beautiful job photographing about 20 years ago. This is a gorgeous nebula. It's a star-forming region. You can see it's just, you know, there's loads of stars, especially those bright ones up and to the right of the actual pillars there. I mean, the whole field is loaded with stars because, again, it's embedded in the Milky Way. In fact, this nebula is about the same distance away from us as the Terrifid, which I just showed you a few minutes ago. Still a little bit farther, about 5,700 light years away. And this is a gorgeous region there. You can see here the pillars themselves. They're about 4 or 5 light years in length, so they're huge structures. And there's an even larger one here called the Fairy, which is about, I believe it's about 18 light years in length. So just an enormous structure. And what these pillars are again, a dense agglomeration of dust that is collapsing to form new stars. In fact, these pillars have been looked at in infrared, and we can actually see these stars in the process of forming. Visual wavelengths, though, the dust is too opaque to let us see within that pillar. So that's the beauty of doing it in infrared. I've got a closer vision of this. But yeah, I'll just mention, I photographed this with my 190 millimeter Maksutov Newtonian. I love that telescope. It's nice and fast, so it's like 7.5 inch f5.3, and that's with a Canon 60DA camera. This next one I've got of it is a little bit closer. There we go. And this was taken with my old 10-inch Meade LX200, which is actually kind of a special version of that telescope. It's the f6.3 version. And I was using an Orion Deep Space Imager 3 for this particular image. What I like about this, this is a CCD camera. I find that just the color rendition it's a lot easier to separate, especially when you're shooting with filters. So you see a lot more of the color contrast between the various structures. And again, this is the top of the ferry that I was telling you about. And the pillars themselves says, again, 4 to 5 light years in length there. What I also like about this is these dark blobs here that you can see. These are Bok globules, and they are actually stars that are in the process of being born there. They're still shrouded by the dust from which they collapsed, and in the not too distant future, when those stars actually are dense enough and hot enough to ignite nuclear fusion at their cores, it'll blow that dust away, and we'll see new stars where the Bok globules are. The pillars themselves are actually being eroded by the intense radiation of this cluster of newborn stars, which is in the same vicinity. They're all formed within the same nebula. So this is just blasting away at the tops of these pillars. And in the Hubble image themselves, if you look at that, you can see it almost looks like the tops of the pillars are just frothing. And it's believed that this process will continue. This erosion will continue, and somewhere in the neighborhood of 50 to 100,000 years from now, these pillars will be completely eroded away. It was believed relatively recently that a supernova shock wave that occurred in this area was eroding them even faster, and that there was some speculation that these pillars would be gone in less than 10,000 years. But interestingly, the Hubble imaged these back about 20 years ago, and then re-imaged them with better cameras after one of its refurbishing missions. Re-imaged them I think about a dozen years later, and by comparing the two images from Hubble, it was realized that now the rate of erosion of those pillars is not due to any previous supernova blast, but is instead they're just being eroded by the UV radiation coming off those bright stars above it. So just a beautiful and very dynamic formation. And again, it's in the Milky Way, not far from the Terrific, a little bit higher up in the sky, better for our latitude certainly, and just a nice object to see. But check it out from if you've got a telescope as well. There, it's not too far actually from M17, the Swan Nebula, which I find visually is a more attractive beast to look at. Thank you.
Okay, thank you, Paul. I'm good. Turn control over to Chris. There we go.
On behalf of all the panelists and all the people who've been attending today, a big thank you to Dave. He's not only committed 2 hours in his hosting role today, he's committed 2 hours for long presentations, and I think he's been involved the whole way along. So fantastic dedication and leadership. Thanks so much, Dave.
Thanks, Chris. Well, it's time for me to hit the hay. I've got to get a teenager up for his first aid training tomorrow morning. So
thank you, Dave.
Have a good night. Stay safe.
I can jump in, guys, if you'd like.
Wonderful. Go ahead, Lance.
All right, I've got some live images here. So just been working on M64. I'll share my screen.
Fabulous.
Not great conditions, but hey. I'll just show you a couple of screen captures I just took. So M64, called the Black Eye Galaxy, spiral galaxy in Coma Berenices, and there's an image we just took here. So the the thing with the Black Eye Galaxy, the distinguishing feature is this dark dust lane right next to the core of the galaxy. My tracking started to go a little crazy on me here. So that's when you start to see the stars trailing like that. It's centered on the object, one of the limitations of the alt-az mounts at times. What I can do, I'll go back to Mellencamp Sky. So this is the object. I'm in video mode now, so I'm taking a 3.7 second exposure here. Lots of noise in the image. So what we'll do is we'll go to a little longer exposure. We'll start at 3 seconds. We'll start that. And then we'll start our stacking process here. And you'll see as the stack occurs, the noise will be eliminated from the image. So we've got one output down here. I'll just stop it there, and then we'll increase the exposure here a bit. Not quite as good of an image as I had at this stage the other time, so I may have some clouds starting to come in, but you can just start to see that's the core of the galaxy. You can start to see that dark dust lane there. I'll let that run. But M64, commonly known as the Black Eye Galaxy because of the spectacular dark band of absorbing dust in front of the galaxy's bright nucleus. Just going to adjust this again here. Yeah, conditions are starting to deteriorate a little bit here, but it was discovered by Edward Peugeot in March of 1779, and the dark dust feature was discovered by William Herschel, who observed it in 1785 and 1789. It's a very well-known object among amateur astronomers, visible even in small telescopes and can be glimpsed with good binoculars. Yeah, that's not getting a lot better. I'm going to go back to one of my other saved images here, guys. I promise you that was just a few minutes ago. That's magnitude 8.5. It has an irregular shape with a very uneven brightness and texture. A very bright, large core. It lies at a distance of approximately 17 million light years and is approximately 48,000 light years across. At first glance, it seems to be a fairly normal spiral galaxy. However, recent studies have led to the discovery that the interstellar gas in M64's outer regions rotates in the opposite direction from the gas and stars in the inner region, which is quite unusual. The inner region has a radius of about 3,000 light years, while the outer section extends another 40,000 light years. An active formation of new stars is occurring in the shear region, where the oppositely rotating gases collide and are compressed and contract. Astronomers believe that the oppositely rotating gas arose when M64 absorbed a satellite galaxy that collided with it, perhaps more than 1 billion years ago. The small galaxy that impinged on its neighbor has now been almost completely destroyed. Its stars have either merged with the main galaxy or scattered into space, but signs of the collision persist in the backward motion of gas at the outer edge of M64. So yeah, that's M64, sort of an interesting aspect to it there with the different rotations of its gases. That's all.
Thanks, Lance. Gabriel mentioned that he's ready to jump in and show something.
Yeah, exactly. Can you hear me well?
Yes.
Perfect. I currently have my telescope that's running, but it's very cloudy here over in Aylmer. So I'll just share a few things. Can you just make me co-host so I can share a screen?
You can go ahead. We just have to stop the screen sharing from.
Sorry, guys. There we go.
All right. So we talked a lot about using small scope for astrophotography, but I'm going to show you what we can do using like a way bigger scope. I'm not using a RASC Hyperstar. I'm using it at the full focal length. I'm usually shooting at 2000 something millimeter. Just to give you an example, what can be done with that. I'm usually shooting nebulas with mono filters, so I usually get something like this once everything is done. Just to give you an idea what can be done if you're willing to go out in winter. In the cold of January, you do have a couple of very, very bright and beautiful nebulas that you can do. This one I remember when I did it, it was like -20, -25. So yeah, very, very cold out, but it's very rewarding once you finish working on them. Another couple of examples. This was done with a much smaller telescope, but it's the Wizard Nebula. Oh, it just froze on mine. Okay, there we go. This is done with like a 4-inch refractor. I think it was in November. Obviously, when you use filters and a mono camera, it gives you like way more flexibility into what you can do to push the colors, but they're not really representative of what you get straight from the camera. I've prepared something just to show you. Once I have the data, what the data looks like once it's fresh, once it's out, before we put all the colors back. Just to give you an example, this one would be a good example. So because the camera is mono, what you usually get out of the sensor is something like this, which is basically what you will be working with to push what you can do with the data. But this is once it's stacked, and it's a mono stack, obviously. But this is just the hydrogen. Because it's a mono camera, you can really isolate what you want to keep with each filter, and this gives you again more flexibility in what you can do. So yeah, it's just a couple of examples of what can be done within. I'm not in the country. I'm in Aylmer, so I'm still in a Boyle 5 to 4-ish sky. Visually, it's impossible to. It's really hard, but with astrophotography, because you're integrating like so much time, you can get away with doing it with being like semi-urban. Usually, my project runs from like 15 to 20 hours of integration, which means I'll work on the same object for like 5, 6, or even sometimes 7 nights if we don't have clouds, obviously. But yeah, this is just a quick example. If this, I'm not sure how long we'll be running, but there might be some opening in the sky later on tonight. But I'm leaving my scope on. If I have a spot, I'll let you know if it clears out more on my end.
Thank you, Gabriel. And do we have someone else ready to jump in with the next image?
I have something.
Please go ahead, Jim.
Okay. Thank you. Now, where did that come from? Share screen. Okay. So this is M1, the Crab Nebula. And this nebula is in the constellation Taurus. It was discovered by an English astronomer named John Bevis in 1731. And it corresponds to a bright supernova recorded by the Chinese astronomers in 1054. The nebula was the first astronomical object identified historically as a supernova explosion. The nebula lies in the Perseus arm of the Milky Way galaxy at a distance of approximately 6,500 light years from Earth. At the center of the nebula lies a Crab pulsar, or a neutron star, between 28 and 30, rotates between 28 and 30 times the spin rate. What do I have here? Sorry about that. 30 times per second it's rotating. And it emits pulses of radiation from gamma rays to radio waves. In visible light, the Crab Nebula consists of broadly oval-shaped massive filaments, which is what you're seeing. And the filaments, from what I've read, are remnants of the progenitor star's atmosphere and consist largely of ionized helium, hydrogen, along with carbon, oxygen, nitrogen, iron, neon, and sulfur. Thank you.
Okay, thank you, Jim. We have Andrea ready to show us some nebula.
All right, here I come. I'm going to share the screen. Okay, there we are. So just quickly, this image that I'm going to show, the first one is with a very small telescope. And I know Simon talked about the wide view. Well, this camera will give you a wide view. And this is a very wide view of a region in the constellation of Auriga. Auriga is a winter constellation. It's very high in the sky all winter. It is starting to set now towards the north. And this particular area has a lot going on. In the upper left-hand corner, that is the same area that Simon showed you earlier. It's M38, a big star cluster with a little smaller star cluster beside it. Over on the far right is the Flaming Star Nebula, and it's very big and very dramatic. And then in the middle at the bottom is the Tadpole Nebula, another very famous nebula. These nebulas are not so easy to see visually. They appear very bright in photography. And this is a 250 millimeter telescope, so quite a broad view. And it's also a fairly big sensor, which makes it a wider field of view. This was taken with a filter, which will try to block out most of the light other than light that comes in on the oxygen and hydrogen spectrum. And I'm just going to do what Paul does, and now I'm going to zoom in some more. And this is a close-up of the Tadpole Nebula. And it's called the Tadpole Nebula because of the tadpole-shaped globules that are up and to the upper left corner of this image. Now this, it has quite dramatic color in it, and as Gabriel alluded to, the different colors represent different wavelengths. And when we process them, we try to develop the color in a way that emphasizes certain features. And in this case, all of the blue surrounding the tadpoles, it came in a different light. So I tried to make it more of a contrasting color to better show up the tadpoles. And the tadpoles are believed to be related to, there's a star cluster at the center, and there's a star forming region. And the tadpoles are some sculpted by winds and radiation, and their heads are basically ionized gas that's very bright. And the Tadpole Nebulas, it's a famous image to photograph, and it's lots of fun because they literally are little tadpoles. That's all I have.
Andrea, you said that this is a small part of the previous widescreen image. So have you just zoomed into a small part, or is this a very different image with a different setup?
Oh, sorry. Yes, I should say that. Totally different image. Because telescopes are not like cameras. We cannot zoom in and zoom out. So telescopes are fixed. So to do a wide field, I need a totally different telescope. And then to zoom in, you need a whole other telescope for the most part. So this was done with the Hyperstar. Whereas the previous wide field image was done with the little small red refractor. I should have clarified that. Thanks, Chris.
Thanks, Andrea. I thought maybe you had just cropped and expanded on a small part of your image, but no.
Oh yeah, no, it's very different.
In the meantime, while you've been doing this, skies have improved for Lance, and he's ready to go back and resume where he was.
Yeah, I stepped outside the dome there as I had M64 last time, and clouds covered that part of the sky. So I found another sucker hole here around the Big Dipper. So we've got a stack going of M82. And it's, much better conditions in this part of the sky. So yeah, I've got that up to 12-second exposure right now. I thought maybe we could just let the exposure go for a stack for a little bit longer here.
What's your exposure time, Lance?
So I started this one at about 4 seconds, and I've been going about 10 stacks each time. Then I went up to 8. Now I'm at 12. So I'm at 24 stacks here now. I'm starting to get a little bit of rotation there. But I'll just try zooming in here. Yeah, just some background on M82. It's Ursa Major in the Big Dipper constellation, about 12 million light years away. M82 is a remarkable, peculiar galaxy. It was discovered along with its partner M81 by Johann Bode, and both galaxies are sometimes known as Bode's nebulae. This one's also called the Cigar Galaxy. It's been spectacularly disturbed by a relatively recent encounter with M81 and displays conspicuous dust lanes and heavy star formation. It is the prototype irregular starburst disk galaxy. Just go back to my last image I took of it there. Might be a little clearer. It was discovered 1774. It's one of the few Messier objects to which William Herschel assigned a catalog number. Herschel usually carefully avoided giving his numbers to Messier's objects. William Parsons, the 3rd Earl of Ross, was the first to remark on the dark dust lanes and patches visible in the central part of M82. Halton Arp included M82 as number 337 in his catalog of peculiar galaxies. It's relatively bright at magnitude 8.4. It appears only 38 arc minutes north of M81 and can be seen in the same field of view with binoculars or a low-power telescope. It has a 9-minute by 4 arc minute halo, contains a 5 arc minute wide core extended along its major axis. Because of the high surface brightness, the halo has a well-defined outline. The core is very irregular in profile and severed into 2 almost equally long parts by a diagonal dark band, which you can see in the image there. Supernova 2004 AM was discovered in M82. An image is taken at the Lick Observatory in 2003, and there was also supernova in 2008 detected by radio observations. It's separated from M81 by at least 130,000 light years. The core seems to have suffered dramatically from several close encounters with M81, most recently about 100 million years ago. The Chandra X-ray Observatory detected fluctuating X-ray emissions from an intermediate mass black hole of roughly 200 to 5,000 solar masses, approximately 600 light years away from the center of M82. Like most galaxies, it hosts a supermassive black hole at the center with a mass of approximately 30 million solar masses. It is much brighter at infrared wavelengths than it is in the visible part of the spectrum. And in fact, it is one of the brightest infrared galaxies in the sky. So yeah, that's M82 tonight. Thanks.
That's very nice.
Great to have live images during this session. Thanks, Lance.
Yeah.
I have a non-live image for you.
Please go ahead, Simon.
Before I get to it, Andrea asked me to show her my the small telescope again. This is my 50 millimeter Evo Guide Skywatcher scope, and that is a small Malincan camera. It's the 287 monochrome, and as I said, that's my mouse for scale. Let me go to the picture I wanted to show you, which is this. This, of course, is the Andromeda Galaxy. This was taken from the backyard here in downtown Ottawa using that very same telescope and camera setup. Here's another image of the same galaxy. This was with a 120 millimeter refractor and a much larger camera. Frankly, this setup, this more modest setup, competes rather nicely with this one here. You can see that there are companion galaxies. This is the Andromeda Galaxy here, end to end. It's a large spiral galaxy. It's our nearest neighbor in terms of big galaxies. It's only about 2.5, 3, maybe a little bit more million light years away, which sounds like a lot, but it's actually right next door. And here's the good news, it's heading straight for us. It'll probably collide, actually it won't collide, it'll swing by very, very close and make a real mess of our galaxy as it does so. But the even better news is that won't happen for another couple of billion years, so don't sell the farm yet. This galaxy here, which is technically known as M32, and this galaxy here, known as M110, they are the equivalent of the Leo dwarf galaxy that Jim was telling us about, except that they are dwarfs, small galaxies around Andromeda. So Andromeda is a group of galaxies heading for us. Just to put this into perspective in terms of how long it takes to capture these images, Lance was showing us that he was using captures of about anywhere between 4 and 12 seconds. This, with my small setup, is a capture of 20 seconds. Obviously, it's a stack, but within 20 seconds, you can already see a lot of this. By stacking, you don't actually increase the signal, you decrease the background noise here. And so you bring out the details like these dark dust lanes, which are actually separating the arms of the spiral galaxy. And the galaxy here is actually viewed not edge on, not face on, it's oblique, which is why it looks so much shorter in this direction and so much longer in that direction. It really is, in fact, the twin of, we think, of our galaxy, but seen obliquely on. And as I say, this is the same thing. There's M32, there's M110, and you can see the dark lanes. You'll probably see more of the outer disk here, but as I say, this is a much larger camera, much larger telescope, and this was not downtown. This was from out under a relatively good dark site. So small camera, small telescope, small price, big reward in a short time frame. Thanks.
Maybe, Simon, you can talk a bit about the fact that this is one of the rare galaxies we can see moderately well with binoculars, and even 32 and 110 faintly.
Worse than that, Chris. I say worse, given that I'm well past my middle age. The younger folk among us can actually look up under a reasonably dark sky and see a very faint fuzzy patch in the sky, and it is indeed this galaxy. The ancient Greeks knew that this was there. They didn't know it was a galaxy, but they knew there was a patch of light up in the sky. Of course, with binoculars, it really does become quite obvious, and even small bird watching binoculars will achieve this. You want to steady them. You might want to lean up against, I don't know, your car roof or something, or your fence, with your elbows on it to steady your binoculars, but you will be able to see, most certainly be able to see this component here. I doubt you'll be able to see this with binoculars. I don't think you'll be able to see these dark lanes. But there's no mistaking that you'll be looking at something which is very obviously not a star. I don't think you'll see this galaxy, and I don't think you'll see that one. You will need a telescope to see those.
And is it considered, I believe, the most distant object that we can see from or with our naked eye?
That's true, Chris. That some of us can see. I have been under dark sky sites, and people have said, "Look, there it is," and I have looked, and I have looked, and I have breathed deeply to oxygenate my eyes and all the usual tricks. And I'm afraid I still can't see it. I need help.
Thank you, Simon. Do we have someone ready to jump in the next image?
I have another one for you, Chris.
Okay, I heard Jim first, and then Paul,
Okay.
you can stand by and wait for Jim to finish. And then you
no
next.
worries.
All right, I'm sort of picking up where Paul left off, actually, in one of his earlier images of the Trifid Nebula. So this is a wide view of the area around the larger nebula in the area called M8, the Lagoon Nebula. This image was captured using the same telescope that Simon has been talking about. It's a 50 millimeter diameter telescope, but using my DS432 camera. So a bit higher resolution camera than what Simon uses. So it's interesting to look at these objects in a wide field of view, to put it all into context, to understand how it relates to the other objects around it. So the next few images, I'm going to zoom in progressively, basically moving from one telescope to the next. So the next image is with a color camera now, but on a 2.5 inch or a 67 millimeter diameter refractor. So you can see a little bit more detail of the gas and dust around M8. You can also see now a bit more detail of the dark nodules that are inside the nebula. We'll get a better look at them later. But you can also see there's another smaller, less obvious star forming region in the upper left. So this is all kind of part of the same large cloud of gas and dust. And it's in the direction of the center of our galaxy in the constellation Sagittarius. So going in one more notch, this is going to a 98 millimeter refractor, so 4-inch scope. So we can start to see even more detail in the nebula. The shock fronts that Simon mentioned when we were looking at the North American Nebula, they're quite obvious now. I can just draw some lines in here to kind of show, that there's quite a well-defined line. It almost looks like a clamshell opening up as the pressure from the radiation from the young hot stars in the new cluster push against the outer envelope of dust and gas and peel it open, sort of like peeling the skin off of a grape or whatever. So there's even another shock front right in there. So that's the edge of the expanding cloud of radiation and solar wind coming off of these hot young stars in the cluster in the middle, pushing against the cloud that surrounds it. And you can also see some quite dark nodules, and you'll get a better look at them in my final image, which is zoomed right in. So this is on my 10-inch Ritchie Chrétien, same camera as the last two views, but now at quite a bit longer focal length. So now you can really see sort of there's almost a three-dimensional aspect, like there's layers and layers of gas over top of each other. The shock fronts are very clearly defined. And these dark globules are very striking, very highly contrasted against the energized gas behind them. And each of these globules, and I'll even zoom in a bit more to 100%. Like, take a look at the these little specks here. Each of those are one of these so-called Bok globules, named after a astronomer, last name Bok, B-O-K. I think he was Dutch. He's the one that came up with this notion that these very dense balls of dust and gas is part of the process of a new star forming. So even though there's lots of radiation and solar wind in these areas, or stellar wind, I guess, to be more precise, gravity has started to collapse that particular ball of dust to the point where it's able to resist being blown apart by all of the radiation around it. So those globules are on their way to becoming stars. So that's quite fascinating. Now, if you're wondering why this nebula has the name the Lagoon Nebula, it's because when you look at this object in an eyepiece, get my pen out here again, this area right here is quite visible as just a dark area in the nebula. And then this area here and here is quite a bit brighter. So I guess somebody in the past thought that the dark lane cutting through the bright areas looked like a lagoon. So that's why it has the name Lagoon Nebula. And that's it for me. Thank you. Oh, a few quick stats. It's about 55 by 20 light years in size, so quite large, and about 5,000 light years away, roughly. All right, thank you.
Great, thanks, Jim. And Paul, you said that you're ready with something.
Okay, I'll just switch over my screen. You good with that?
Excellent. Go ahead.
Okay, so this is sort of continuing on what I was showing you in the Eagle Nebula with the pillars of formation. This is a similar structure. This is in the nebula IC 1396 in the constellation of Cephus, and it's called the Elephant Trunk. This nebula, or this dark column of gas, is again several light years long, so it's quite a large structure. And this image, I took this using narrowband filters. The narrowband filters are they really allow you to separate the different elements that are generating the light within a nebula like this. I've taken pictures of the same region in broadband, and so it's with a regular camera, regular RGB filters, and all the lit up areas that you see here are predominantly red. So I find that with the narrow band filters, you get a much more three-dimensional view, certainly of, you can see for instance here, the apparent hazing coming off the columns as well. And what furthermore, the narrowband filters are cool in that they actually allow you to glean some information as to what it is you're looking at here, because the narrowband filters are for those that aren't familiar with the concept, they isolate just a very, very narrow portion of the visible spectrum, emission lines basically generated by certain specific elements. So what you see here is all the blue areas, the bluish areas that you see here originate from oxygen in this nebula, oxygen atoms and molecules in this nebula. The greenish areas are hydrogen. You can see interspersed through there, and the reddish, the reddish, like the dusty areas here, the reddish areas, and the yellow. These are sulfur. So it's an interesting mix of elements in here. The other colors in between are combinations of those elements intermixed within the clouds itself. So the nebula itself is about 2,400 light years from here, and again, continuing in the vein of several of the folks that have shown images here. This was taken actually with a very small telescope. This is using my 70 millimeter stellar view Apo. So the lens on this is just under 3 inches in diameter, so not a big telescope. And I was using an Orion Deep Space Monochrome Imager 3. So a relatively, it's one of my older cameras and has a relatively smaller chip. But for this object, which is fairly large in the sky, and made it to that particular telescope, it gave me the field of view that I wanted to really focus in on this beautiful structure. And this is a combined image. When you do narrowband, you tend to have to expose a lot longer because you're just looking at such thin slivers of light. This is a 5-hour exposure in total with the 3 filters. Thank you.
Okay, thank you, Paul. And Andrea has a bubble to show us.
I do. Hang on. I'm going to share my screen. So one of the things that, oops, Paul, you have to stop sharing your screen.
Oh,
Okay.
I just stopped it for him.
Yeah, I was
There we
just
go.
actually going to.
Share. Okay, can you hear me?
Yes, we can hear you. We can
All
see
right,
your red scope.
Yeah, so it's the red scope. So I when I first heard about the bubble nebula, I was kind of obsessed, and I thought this would be a wonderful target to go for. And so I used this little tiny scope to go after the bubble nebula. And I'm going to show you the results were not exactly inspiring. Whoops, I went the wrong way. So this was what I got with my telescope and a DSLR. This smudge at the top is the bubble nebula. And there's actually a star cluster down below called M52. So I was kind of disappointed and I didn't think much about this nebula. And then when I got my hyperstar delivered, which allowed me to do a deeper field of view, a more focused field of view, I had quite different results. And so this is what I had. This was my very first image that I did with the hyperstar. And needless to say, I was quite thrilled because I actually could see an actual bubble, which is, there is a central, very, very hot star within the bubble, and it is sending out all kinds of radiation and it's just sending all this material out in the form of a bubble. And so that's exactly what it is. And like Paul mentioned before, these areas of space are full of hydrogen and oxygen. And this was shot with the hyperstar, but using a filter, the L-enhanced filter, which only allows hydrogen and oxygen to come through. And it's a very big nebula, 7 light years across, but in the wrong telescope, it's extremely small. But if you get the right telescope, you too can have a lovely bubble nebula image like this one. So that's all I have to say about this one.
Great. Thanks, Andrea. And while you've been doing that, Lance is having more success stacking images at his end. So Lance,
Wonderful.
over to you.
All right. I moved a short distance from M82 over to M81, the other part of the pair of Bode's nebulae. So actually, this is a new stack I just started here. Let me see. Just going to increase the exposure up to 10 seconds here. And maybe we can just watch this build. We can see some of the details come out here. So you might remember in some of my earlier images, we were starting to see some star trailing. And what happens with this software when you're stacking, there's two different stacking modes. I was using planetary, where the software focuses on the deep sky object itself and not so much on the whole star field. So you tend to get the object looking good, but the stars will start to trail. Now I'm using what's called deep sky mode. So it's basically taking the whole field of view. I may not be using the right terms here, but it's taking the whole field, the whole star field, and focusing and matching those. So you'll see as the exposure moves along, you won't see the star trailing. And the downside to this is I find I have to have pretty good conditions, because if the software can't pick up enough, all the stars to a certain extent, we get what we affectionately call within the group the Pink Floyd effect. And maybe I could let this run here. It'll probably kick in a few frames. And that what happens there is if the software gets to the point where it says, I just can't follow everything, the sky's not dark enough or it's not clear enough, it's, it sort of breaks down and you get to see the what we call Pink Floyd. But we're up to 16 stacks here, and we see some nice detail coming into M81 here. You can see some dust lanes here next to the core, and you can start to see the outer arms here. I ran a stack there while Andrea and Paul were talking, and I was doing it about the same settings here, and it was around 25, 26 that Mr. Floyd showed up. We're at 18 now. I'll just stop it here and increase.
Yeah, get a single frame. Get a single frame first.
Sorry, Jim.
What I do when I'm doing deep sky stacking is when it's looking good, I snap a picture of it. Because I never know when
doing that, but I just snapped a couple, Jim, there a few minutes ago. But
exactly, because you never know when Mr. Floyd is going to occur. Now this image looks like a wonderful image where a little bit of post-processing or is really going to bring out those spiral arms. That's a wonderful capture you have.
Yeah, thanks, Jim. There it is.
There it is.
There's Mr. Pink. But that's what happens, guys, when the software loses track and you get all these rays coming out here. So, but just to show you again. There was the one I snapped on the last stack just before Pink Floyd showed up.
That's excellent.
Was anybody else going to talk about M81?
I think you should use the chance to do it.
Okay. A little bit of background on M81. Just be a second here. M81 and Ursa Major, one of the most conspicuous spiral galaxies in the sky, forms a physical pair with its neighbor M82 and is the dominant galaxy of the M81 group. One of the easiest and most rewarding galaxies for amateur astronomers in the Northern Hemisphere. Bode, when he discovered it in 1774, described it as a nebulous patch, which appears mostly round and has a dense nucleus in the middle. Total visual magnitude of 6.8. M81 can easily be found with binoculars and small telescopes. Under exceptional seeing conditions, it has even been glimpsed with the naked eye. I've never heard of that before, but appears as an elongated, diffuse 20 arc minute by 10 arc minute oval patch in small telescopes. Its periphery has quite low surface brightness. With averted vision, broad, diffuse, indistinct spiral arms can be glimpsed. It's probably about 12 million light years away, as determined by the Hubble Space Telescope observations of Cepheid variable stars within it. The true diameter is at least 70,000 light years. Its mass has been calculated to be around 250 billion suns, makes it somewhat heavier than our Milky Way. M81 is the brightest of a group of 34 galaxies called the Messier 81 galaxy group. The distance to the center of the cluster is about 12 million light years. It is the second nearest galaxy group to our local group, after the Sculptor galaxy group, which is about 8 million light years away. Then they talk a little bit about the encounter with M82 also. Only one supernova in 1993 was discovered in M81 by a fellow in Spain. It reached a magnitude of about 10.5 and the second brightest supernova observed in the 20th century. That may be out of date now, I'm not sure. In 1995, astronomers found about 70 candidate globular clusters in the region around M81 and estimated a total population of 210 globular clusters. So yeah, that's M81. Thanks.
Did I hear you say correctly that someone claimed to have seen it naked eye? If only
yeah.
dark skies.
Like I say, Chris, I've never heard of that before. I don't know if anybody else has, but
Well, I read
Simon, have you seen that with your naked eye?
Yeah, right.
Yeah. But I read that it's observable in binoculars. Has a very faint patch of light.
Can I ask, Lance, what is your focal length here? I think I missed your equipment, but this is a very deep image, is it not?
Yeah, that's I've got my CPC 11-inch. It's 2850 millimeters. So.
Oh, amazing. No reducer?
Thanks. Pardon?
No reducer?
Yes, I have a yes, I have a reducer. So what is that reducer, Jim? It's about a 0.5, similar to the universe reducer.
Yeah, about 0.5.
Yeah, okay. So it's about a 0.5 reducer, Andrea, on there.
Oh, excellent. Very nice.
Thanks.
I see it's 10:50, so we still have time for one or two more, but we are approaching the end. Do we have someone with some last images ready to share?
I have something I can share.
Okay, Mr. Thompson.
So this is a wide field view of sort of multiple objects, but collectively it's referred to as the Veil Nebula. It's up in one of the wings of Cygnus the Swan, so it's quite a popular object to observe in the summertime. So this is a remnant of a supernova that happened quite a long time ago and has had time to spread out and kind of thin out. When you compare this to the Crab Nebula that Jim showed earlier, this is a much older object. So it's about 65 light years across, and it's about 2,400 light years away. It's thought to be the remains from a star about 20 times the mass of our star that went supernova between 10 and 20,000 years ago. At the distance this object is away from us, the supernova would have been bright enough to see during the daytime. So quite bright. So this particular view, it was captured in that 50 millimeter scope that Simon and I like so much. I believe there were 20-second exposures, about 30 of them stacked. So on the order of 10 minutes of total exposure time. And I was using a dual band light pollution filter, so a fairly narrow filter, because this was captured from my backyard here in the middle of the city. So I have a few zoomed in shots to kind of show a bit more detail. This is a zoomed in on the eastern veil, the eastern part. It's the brighter of the three main chunks. And you can see in this color image now that there's actually several different types of gas that is emitting light in this area. There's a very strong green emission from oxygen and a strong red emission from hydrogen. So this is definitely an object that is lovely to observe with a one-shot color camera. Now, if we zoom in a little bit further on the lower part, you can see even more intricate detail on this object. This was captured on my 10-inch Ritchie Chrétien focal reducer, bring it down to about f6 and a half, somewhere around there. So yeah, lots of lovely, lovely, delicate detail. And you can even see how the hydrogen alpha, especially up in the upper part, has sort of a different, especially here, this has kind of a fluffy cotton candy kind of look to it. But the oxygen 3 has a more sharp, stringy kind of texture. It's kind of interesting. The other main parts of this nebula, the western part, the western veil, has a bit of a different look to it. It's sometimes referred to as the witch's broom. But again, you can see intricate interplay of the hydrogen and the oxygen 3. Zoom in a bit further, you can see even again a bit more detail, kind of the puffy cloud-like appearance of the hydrogen alpha emission, but the more stringy, sharply defined oxygen 3. It's kind of neat. And the final view I have is of the third part. It's quite a bit fainter than the other two. It's referred to as Pickering's triangle. It's a roughly triangular shaped area, but again, delicate interplay of greens and reds. So a lovely, lovely nebula to observe. It's quite large, so you do need shorter focal lengths to see the whole thing.
So Jim, what filter were you using if you were using a filter?
Oh, definitely using a filter. All these images were captured from my backyard, so definitely had to use a light pollution filter. I believe they were all captured, let me think. I think they were all captured with a Optolong L Extreme, if I'm not mistaken. It was either an L Extreme or an L Enhance. It depends on when they were captured.
Kind of looks like the L Enhance, but I know you have an Extreme, so
it could be, yeah. The green is quite strong, so it could be the L Enhance also. I don't remember, but it's one of those two Optolong filters. That's it. Thank you.
Jim, we have one final unusual image, a short image presentation by Paul, if that's an oxymoron. And then we'll move to closing remarks from Jim.
Sure.
Paul?
What are you saying, Chris? What are you saying?
I'm just noticing the time of 10:57.
Okay, I'll make it short. I wanted to show this one because it's unusual. I've shown this at one of our meetings. I shot this a couple of years ago. And it's not something that you can see with a lot of deep sky imagery, because most of the stuff that we look at when we look at all these galaxies and nebulas is very static. You look at it 1 year and 5 years later, it looks pretty much the same. This is a really weird object. It was discovered in 1783 by William Herschel, and it's called Hubble's Variable Nebula. It took me 5 months to photograph this. And what I had to do is shoot whenever it was clear, whether the sky was great or not, to get this time-lapse effect, and I'll let it run here. I hope this works because it is a bit of video here. Hello, there we go. Can you see the motion in that?
Video's coming through well.
Awesome. So this is just going to loop, and it's going in one direction, and then I reverse it and it goes in the other direction. And you can see the tendrils moving here. And what this is a very hot star at the tip of this structure. The cone itself is about a light year long, and what this star that's in the tip here is believed to be very hot and very young, and it's got dust clouds in orbit around it. Coalescing probably into a planetary system sometime in the near future. But these dust clouds are dense enough that when they come into the appropriate line of sight, they'll actually block out some of the starlight from the actual star and cast shadows on the cone. And that's what you're seeing shadows moving across this cone of material from this nebula. It's quite a fascinating object. And when you see it in a telescope, it's not very big, and it looks like a small comet, but it is Hubble's Variable Nebula. And this is a 5-month-long time lapse. And I will end it there.
That's really neat, Paul, was, as you said, we don't normally expect to see motion or change in deep sky objects. So nice to have a new perspective. So
Thank you.
We'll switch back to Jim for some closing remarks.
Great. Thank you, Chris. So I'd like to thank everyone who made this possible, all the presenters who we've heard from today, all the people working in the background to keep things running smoothly, like Chris and Dave and the other people working as co-hosts. Without all of these volunteers working together to make this happen, it just wouldn't have been. It's great to be amongst such a great group of talented and passionate people sharing a common interest in astronomy and a desire to share that interest with the public. So I hope we've inspired a few people out there to pick up astronomy as a hobby, and maybe we'll see you in the future at a RASC or an OAOJ meeting. So thank you very much, everyone.
And thanks, Jim. Well, it's been very kind of you to thank and mention some of the other people who've helped. You've really been the leader for 2 years in a row now that came up with the idea, brought everyone together, came up with all the subjects, and have made 2 wonderful days. So thanks so much for your great leadership on this, Jim.
For how great it's been and how successful it's been, I hope we don't see each other again next year. I hope we're back to in person by
person on a sidewalk during the day and then again at night.
Yeah, like the old days.
Like the old days, yeah. Seems like really old days. Yeah.
Oh, bravo.
Thanks and good night, everyone.
Right. Good night.
Night.